All right, let's start timely. I hope you can still hear me on Zoom one last time. Yes. All right, otherwise say something in the chat. Hi, in person as well, you guys. Nice to see you. So this is the third iteration of the Maritime Computer Vision workshop. I'm Benjamin Kiefer, and I'm going to chair this workshop session in person. We have our colleagues, Loise, Mattia, Janis, Mattia, Uma, Chaitra, Arnold, being in the organizing committee, also being online. They're going to present some of their parts as well. And those are just a few of the names that have been part of the organization of this workshop, obviously. So we will have these slides being uploaded to the webpage later. At the very end, you see a list of a lot of people that were helpful in the technical committee, in the program committee, and all sorts. So just so you know, we also record the Zoom meeting. So you're going to be able to hopefully check everything later if there's anything specific. But still feel free to ask a question in between. Yeah, I've given this motivation a couple of times now. You've all seen it, right? Like 70% of the water of the Earth's surface is water, 80% of trade is through ships. That's nothing new, but just to showcase to you also that there's really a demand also in the applications, like in the industry. Here's kind of an illustration of what kind of companies emerged over the last few years that try to do autonomy on the water. Now, in this case, on the water surface. So for example, you have sea machines here, you have Orca AI, Buffalo Automation, Abacus, Captain AI, Cedar AI, and Lookout, just to name a few. And that's just, in my field, kind of for surface vehicles, but it's the same thing also for underwater vehicles. So there's an increasing kind of demand in the market. People want to be able to autonomously do decisions, and yeah, these kinds of companies, they have various use cases. So some of them are for recreational purposes, some of them are for workloads, deliveries, and all that. And they all have one thing in common, and in that they want to be more intelligent. They want to use vision to help them make decisions better. And they're kind of waiting for us, for you guys, to propose nice algorithms, computer vision algorithms, to help reconstruct the scene, generally, like navigate, make decisions, and all that. And yeah, the purpose of this workshop is to kind of raise awareness a little bit and also unite a little bit our community, try to kind of find common things. And I hope this workshop makes a small step in that direction. But without not wanting to bore you anymore, so this is going to be the schedule for today. Yeah, we're going to have the opening, and right after, we're going to have Alex Alahi talking about 7 foundational principles for autonomous mobility. So this is kind of like an inspirational talk in a neighboring domain. I'm going to motivate it in a second again. And we have the challenges, which are going to be from 8:35 to roughly 10. We hope to be finished a little bit earlier so we can have a proper coffee break of like 15 minutes. Let's see about that. And after that, we have 2 more keynotes on underwater computer vision. And finally, we're going to spotlight the accepted papers. And later, we'll have the poster session in person. Yeah, feel free to come here also. Yes.
I've got a question about the schedule. So there is this MaCVi program, the spreadsheet, and we have 4 from 10 or 5, and so it's kind of intersection with the program. So what is the?
So you have to have a little bit of wiggle room. So please be kind of here at the beginning, and then things might get shuffled a little bit, just because if someone doesn't appear or show up, then yeah. All right, then, is there anything from Zoom? Otherwise, I would start directly. So with the first point, so the first point is the keynote from Alex Alahi. He's an associate professor from EPFL, and he's known in the autonomous driving domain for quite some years. He's given a couple of keynotes on CVPR workshops, and has come up more recently with concepts like socially aware AI in the context of autonomous driving and also other contexts. And yeah, the reason why we invited Alex is we believe that the maritime domain has some of the same challenges that we have in the marine domain. And yeah, I hope this talk can serve kind of as an inspirational source, and some of these concepts can maybe even develop in the marine domain, or yeah. So Alex, you here?
Yes.
Welcome. Thank you for, you wanna share your screen?
Yes. Is it working?
I'm gonna have to put you on the other display. Yes, you can see it. Please start, yeah.
Should I start?
Yes, please.
Awesome. Thank you. Thank you for the invitation. Yes, I want to talk about a few principles that we are working in my lab that we believe are quite generic actually to develop autonomous mobility, autonomous platforms, navigation, and let me dive into it by motivating first mobility. And there is this documentary on Netflix that describes life on Earth as quite dependent on mobility. So the concept of life depends on the freedom to move. At any given moment, billions of humans are moving to eat, work, discover, connect. But then the question that we ask ourselves, is it safe, sustainable, and even accessible to all? We know that every year, 1 million of humans die in car accidents due to human errors. These car accidents cost 800 billion per year in the US, and 500,000 of people suffer from spinal cord injuries per year. Can we address all these challenges? Let's look at this road. Some kids came out of the bus and decided to cross the street. What saved the kid is autonomy. AI, and more specifically computer vision, is used to detect objects in real time and control the truck to avoid the collision. Our goal is to bring a safe yet effective mobility for all by advancing autonomy, fostering autonomous mobility. And it's not only for self-driving cars, it's for self-driving trains, self-driving ships, boats, drones, scooters, anything that moves, and even human at the end. Then the question is, do we have the AI to develop autonomous mobility? I'm going to use the autonomous driving as an example. So if we look at the AI of a self-driving car, the first step is perception, detection, detecting everything around the vehicle. And nowadays, this is quite impressive, and we do have working solutions. We do have algorithms that are quite good in detecting all the objects of interest. And then the next step is planning a path accordingly. But then we still have accidents. Well, we still don't have self-driving car operating usually at scale around us. And one reason we believe is the lack of being able to anticipate the future. So when we look at this pedestrian on the right, the AI actually fails to predict what the pedestrian will do in the next second. The pedestrian is static, but it turns out that the pedestrian decided to cross the street to catch the bus. We humans have this capability to predict this, and we believe that we need to develop modules, algorithms that can do a better job in predicting, anticipating the future of all our dynamic agents. So we should introduce another pillar, which is this prediction pillar, this social forecasting pillar. And if we want to better predict the world, we need to maybe rethink how we see what we detect. So if we only detect bounding box or just dots, points, we will not be able to do a good job in necessarily predicting the future of some of these dynamic agents. For instance, in this case, we need to maybe extract the skeleton of these humans, the focus of attention, the eye contact, the orientation, the pose, what kind of action, to be able to better predict and anticipate the future. Let me look at another type of autonomous system for autonomous navigation, a robot navigating this type of crowd. And we can use exactly the same pillars. The first one is detection. We detect everything, and then we try to plan a path according to what we have detected. But again, here we need to develop this capability to understand that even if there are some physical paths that are physically possible, they are not socially accepted. It's not okay to go between two people talking to each other, and we need to anticipate the behavior of the person on the left to not cross path. So there is only one path that is physically and socially accepted, is the one on the right. And this is what our prediction, social forecasting pillar can tell us. And by combining all these pillars, it paves the way to, as Benjamin said, a new type of AI that we refer to as socially aware AI. And we have worked over all these pillars, and our motivation to disentangle all these steps and not do end-to-end navigation, like from an image to the control, is to actually be able to exploit all these pillars across different platforms. So whatever we develop to do detection, perception can be used on a car, but also on a robot, also on a boat or on a drone, and the same thing for prediction and planning. And the way we think about all these pillars is with respect to learning a good representation to solve these tasks. So it's all about representation learning, and I'm going to share basically a few examples. For perception, we have an image, and our goal is to, from the image, extract all these perception tasks. But because we are interested in a real-time solution and potentially computational low-cost solutions with low memory usage, we do want to be able to develop neural network architecture that will do this jointly. Just with one network, we'll be able to extract everything that we need on the perception step. And when we were trying to look for a shared representation, we have to innovate on how we want to combine all these tasks together. How can we handle the gradient in an efficient way, coming from all these different tasks that have different data set, different number of examples, and how to be able to still learn a shared representation without losing performance by combining all these tasks together. So we have more details in one of our paper here, where we show that we can extract 32 attributes without necessarily losing a performance. And these are some examples of what we can extract. We can extract the appearance of the pedestrians, their behavior, but also their intention to potentially, for instance, cross the street or not in this case. Here are some illustrations, some visualization of predicting the intention to cross the street. So whenever it's in blue, we believe that the pedestrian will cross the street. We are also interested in extracting 70 key points on all the objects of interest, not only humans, but also vehicles, bicycles, animals, and so on, and do this all with a single network architecture. And then once we have all these 70 key points, we can also develop different type of neural network that, given skeletons, will actually do 3D reasoning, action, understanding as well. We show that we can locate objects, humans in this case, in 3D given just a single camera that extract 2D skeleton from the image, and from the skeletons extract the depth of these objects. We can also understand like eye contact with this skeleton, but we can also extract scene graph on the potentially relationship between object and humans and the scene. And it was, in fact, this work was presented as WACV a few years ago. But then, what is the current challenges in solving perception tasks is we still struggle to detect rare actions. All these class of objects that we don't necessarily have training data, or we have very limited examples. So it's very difficult to suppose that we can have training for all the possible objects and actions that we might observe in reality. So how can we address that? Now I'm going to talk about it later on. Then for our second pillar, the social forecasting, it's all about learning to predict. So we observe a sequence of trajectories, point in time, coordinate of objects, and we want to predict their next coordinate. And over the years, we have developed many neural network architecture to do that, where we studied also a new way to bring causal reasoning on the representation that we're learning to do this task, how to impose some low rank adaptations. So suppose that you're able to learn to, or you have enough data to learn to predict pedestrians, but you also want to predict a different type of agent, like a bicycle. Can we transfer, can we just fine tune or adapt what you have learned from pedestrians to this new class? And yes, you can by using similar ideas as LoRa or Clora, all these low rank adapters. And then also recently, we show that you can use diffusion model to learn the multimodal representation and have a promptable way to deal with this task, which means that you can use multiple type of modalities for input. It can be just coordinate, but also the skeleton of humans to better predict where they will go. But what's the main limitation of all this forecasting work is that when you do only fully data driven, your performance depends on the distribution of your training data, of whatever data you're collecting. And then you cannot necessarily guarantee that you're able to predict or learn the basics behavior or even the physics behind these dynamic. And we showed in some other work that even if you take state-of-the-art deep learning method that are ranked first in some of these forecasting challenge, they don't necessarily do a good job in predicting some very basic behaviors because they are out of the distribution of the training data. And I'm going to also share a few ideas on how to address this. And finally, on planning, it's very similar to prediction, but you do have access to the goal. You know where you want to go. And we also showed that
Keynote EPFL
to improve the planning performance, if you can bring more labels and generate more synthetic data of wrong behavior, you can actually improve your policy. It's because you usually have actually data from good behaviors, of good interactions, of humans interacting with each other. But if we also supervise our training with some contrastive loss, with examples that are synthetic negative examples, it actually gives a boost to our performance. But yet, nevertheless, we are not very robust to distributional shift. We still struggle to potentially transfer what we have learned from one environment to another one. So these are all the current limitation of our modules. And the question is, how can we move forward and address these challenges? And I suggested 7 principles that we believe can help in moving the field forward in addressing these challenges. So let's look at the first 2, the principle of prediction and the principle of opposites. All these principles are towards what kind of guidelines or thinking can we do to improve the learning of a representation. So it's always in the context of, I want to learn a powerful representation. What kind of supervision, what kind of constraint should I impose on my learning scheme to better learn these tasks? So the first principle is about arguing that a representation that learns to predict sensory input response or the signal itself is a powerful representation to learn other tasks. And this idea is not new. It goes back to 1860. Neuroscientists argue that our brain actively makes prediction about the world based on past experience. And this is what foundation models are about these days. Generative pre-trained transformer, they learn a representation to predict the next signal, the next token. It can be a text, it can be a word, it can be an image. And then they are fine-tuned with the principle of opposite. And the principle of opposite tells us that learning is successful by means of opposite through the contrast of positive and negative example. As Rumi said, things are known by their opposite light by way of darkness. So I believe that representation learning in general can be staged as 2 steps. First, let's learn to predict anything with unlimited labels, and then let's learn specific things with few examples. And then we can potentially detect rare examples and that rely on few examples. So we have started to do this a bit. So we have recently actually developed a foundation model that, given an image, predict the next frame, the next images. We can also look at it as image to video or a word foundation model. We have several input. It can be RGB, but also depth. And here we show that we can develop a method. We have developed actually a model that given an image and some actions on the control on the image, we can generate the next frames, the next the video that comes out of it. We actually developed this based on the stable diffusion architecture, where we show that we can bring some new controls to it. And we trained it with pseudo labels. So we collected a lot of videos from YouTube. I mean, we just used them, about 2,000 hours of video of cars driving around, and then we run algorithms to detect the depth, the skeletons, the objects, the ego trajectories, all with pseudo labels, and we train our image to video transformer to architecture to solve the generative task. And this is, we're not the only one doing that. There was this recent work from NVIDIA, Cosmos, sharing a foundation model. They have used a lot of data, 20 million hours of data, a lot of GPUs, and they have shared their model recently. So we are doing something a bit similar, but with much less data and resources, but with more controllability. And here we are showing you some qualitative result of what we are generating. Again, the input is just one frame, and then we generate the video that comes out of it. So this is an illustration. On the left, it's our input, and we learn to generate the next frames. And we can control, we can say, I want to go right, generate a video that will go right, and I want to go left and generate a video that will go left. There are some other examples. We can also have a control on the content of the image. We can say that I want this motorcycle to go from right to left. This is what we have shared on the left of the reference frame, and then it generates the video accordingly. The same for this car, or suggesting or asking to generate the dynamic of a car, or to move the cars around in our video. We can do the same with pedestrians. We can ask the model to generate when pedestrian will cross the street, how it will look like, or if they stay still. We are generating multi-modalities. So we are also, for instance, generating this depth jointly with the image. So this was the work that we did to develop this self-supervised learning, this foundation model. We also do this with vectorized input with trajectories only, where we're interested in fact learning a foundation model to predict, to generate trajectories. So we did a similar work where we try to unify all the existing data set in the context of autonomous driving, make a unified format, and then train and learn a foundation model with that. The third principle is the principle of multimodality. And again, it's also to motivate it to detect these rare actions. And the way we look at it, we believe that we can interpret the world through multiple senses, and this highlights the importance of leveraging additional source of information. And until recently, neural network architecture were quite different across modalities, such as vision, audio, and NLP. But nowadays, the same architecture, like a transformer network, can deal with all the modalities. So you can learn to align this latent representation between vision and language and benefit from the knowledge available in one of these modality, in this case, LLMs, for instance. And then you can use it to recognize or understand rare actions thanks to the knowledge that you have learned from text. And do zero-shot classification, for instance. And the fourth principle is the principle of residual learning. And this is motivated to address this challenge of not forgetting basic behaviors, or to be able to detect also predict basic behaviors. And the way we motivate it is, as I said, usually nowadays, state-of-the-art prediction method learn the task of prediction from scratch. They use the whole capacity of the network to learn everything about navigation or trajectory prediction. But we do want to use the data to only learn concepts that we struggle to explain, like social norms, for instance, but not necessarily things that we know, like the physics behind it, or like very common behaviors. Why do we don't necessarily need to learn them from data. And so what we're suggesting is to use our knowledge-driven methods or physics-based method as a starting point to solve the task, and augmented with data-driven methods. In other words, to correct the output of knowledge-driven methods with constrained residuals that are learned from the data to be able to update the behavior and only focus on these potentially social norms. And we have shown that we can also do this with vehicle. We know that, for instance, the trajectory of vehicle needs to follow the road, cannot go off-road, has a bit of some physics behind the dynamics. So we use that and then just try to update these knowledge-driven method with our neural networks. The fifth principle is the principle of compositionality. And I like to revisit it as follows, by saying that the world that we see, the collected signals or the perceived concept might look complex at first, but they might be the composition of few simple concepts that you combine together. And the challenge is to find these few concepts, these atoms of a dictionary. For instance, the space of possible interactions and social interactions is large, but it's the composition of few atomic learnable concepts. And by learning them, we can adapt and maybe learn to be less impacted by shift in distribution. The sixth principle is the principle of causality. So our ultimate scientific goal in machine learning is to learn causation, the underlying cause effect. Yet the field of representation learning or learning correlation in the data. So we can study how to learn causal representation by injecting weak causal supervisions. For instance, we can potentially learn in simulation some causal relationship with counterfactual experiments, get this annotation and use this annotation to supervise our learning to better model the causality and transfer whatever we learn into the real world and hope that this actually remains in the real world. And we have shown that, yes, this is possible in a recent work that will be presented in CPR. The last principle is the principle of in vivo practice, which means that in vivo refers to systems that operate in contact to humans, as opposed to in labs. And what we know is that human behavior change in space, across cities, in time, over the years. So it's unrealistic to suppose that whatever we have learned will remain and that distributional shift will not occur. So can we adapt our representation on the fly? So can we develop method that at test time adapt to the dynamics? And what kind of auxiliary self-supervised task we can impose to learn these shift and update our representation on the fly. And there's this field called test time adaptation that is actually studying that. And I think that this is also a very good area, and we should consider it when we develop our system. Voila, all these principles will impact the embedded AI of all our autonomous mobility applications. I want to, so I've talked about like self-driving car, autonomous robot. Let me share maybe one last use case that I think it's super fun. It's on human body. So we use this to help paralyzed human to move again. Humans paralyzed with spinal cord injury. And the way we do that, we use our robot to detect the skeleton of the patient, predict what the patient should do to walk. I mean, what should be the ideal skeleton, and control the electrical stimulation of their muscles to match the ideal behavior. And this is a demo our robot on the left is looking at the patient and controlling the stimulation to his muscle to make the patient move in a way that we believe the patient should move thanks to our prediction module. So I'm going to end here. To sum up, we have all these principles that we want to apply to our 3 pillars and demonstrate their use case across applications. And let me finish with this video. Suppose you have this autonomous vehicle that detects the pedal and the pedestrian. What should the AV do? Avoid the pedal. Shall we make it a hard rule and always avoid a puddle? Well, in some context, the autonomous vehicle should read the humans to splash them. So it's all about AI reading humans. Voila. Thank you. If you have any questions.
Thank you, Alahi. Are there any questions from the audience, either Zoom or in person? Yes. If it's a long question, you can also come here, maybe. You can also try this, but I'm not sure if they're gonna hear it. Maybe. Yeah, to see you also.
Yeah. Well, first of all, congratulations for such a powerful publication. It's an impressive list. My question was about the last principle, the in vivo practice. How is it similar and how is it different from reinforcement learning?
How is it similar or different from what?
From reinforcement learning.
From reinforcement learning?
Yes.
Yes. So the way it is a bit different is in reinforcement learning. Yes. So you have learned a policy, maybe in simulation, or you do have a working policy that will take action in the environment, and even if the environment change a bit. But what if the behavior of your agent has changed and it was not actually in your simulator or you or in whatever data that you had that you try to learn your policies. So the question is, for instance, we have pedestrians that are walking in a specific way. We are simulating that and we're learning good policies to interact with them, but they change their behavior in a way that we did not imagine before. For some reasons, they go faster because of evolution, or they decide to change some rules in navigation, and they do it. How can we, and what can we do with our existing method? How can we adapt them on the fly to react to this change in behavior? So we need to have a mechanism that potentially look at the data on the fly, maybe update its parameters, the model that it has, to handle this shift in distribution. So this is my way to look at it.
Thank you. There's one question in Zoom from Arnold. He asked, would you think reasoning capabilities shown recently in the LLM space are useful for the 7 pillars? Where would you think it would fit well?
I think it's useful for the multimodality pillar. Yes, in fact, here, if we are able to align the representation of an image or a video with some sentences, then if we see something that we're not used to, we can take advantage of how a LLM, the knowledge that exists in a LLM, the reasoning that maybe exists in a LLM to tell us what will happen. For instance, if we see the image of a ball in front of a street and maybe a kid, or we know that there is a school nearby, and we ask the LLM what will happen, the LLM will tell us there is a chance that a kid will come pick up the ball because there is a street, there is a school, and so on. So there is a a bit of a knowledge in the LLM that will help us better predict the future, although we never actually had this in our training data. Does it make sense?
For me, it makes sense. I know that's the answer, but yes, he also agrees. Is there any more question? Otherwise, I have one final question. So my question is about, I'm working with the startup Lookout, and we want to propose paths for boats. And this path depends fundamentally on the paths of other boats, like how do other boats essentially drive? How do they behave? And unlike in the autonomous driving scene, where you have very rigid rules, obviously they're broken also sometimes, but you don't have the concept of lanes, for example, in boats. So it's really hard to predict kind of where another boat is going, and depending on that, where you're supposed to go. And so my question kind of would be, what's your take on, have we solved, let's say, vision enough? Like, is the vision that we currently have, the 3D construction, is that good enough to predict such subtle things like social forecasting? Like for pedestrians, I imagine faces can be really small in image space and pretty far away, and you can barely see whether this person kind of looked at you, whether that person is aware of you. Do you think sensor-wise, vision-wise, we're good enough already to do these things, or do we have to do a better job on that? Yeah, that makes sense.
My safe answer: we're not good enough, so it's easy. So we still have work to do. Otherwise, we're jobless. But then, yes, I think in your own domain, it's a very interesting domain. The causality behind predicting the behavior of other boats, for instance, depends also on the nature of the climate of other data, or the sea that you need to potentially model. But we are showing that we have the methodology to do that. So in our methodology, in a self-driving car, we also use the scene, but it's a bit static. But for humans, we have other cues that are more dynamic. So we have the architecture to handle multiple modalities, multiple input, to learn to predict, as long as we have enough examples. And if we don't have enough example, can we learn from other agents and transfer potentially thanks to a foundation model on prediction? And I think this is where we are going. We're trying to develop a foundation model on prediction, so that, for instance, this one, so that we can, in fact, in other domains, rely on less example, but still do a good job in predicting.
Yeah, that makes sense. Perfect. Yeah. Yeah, I found it really inspirational, especially also like your part about like where you source 2,000 hours of YouTube video. So as part of this company I'm working with, I also learned YouTube is just a source of so many data. So in the marine domain, we oftentimes like complain about few data sets compared to the autonomous driving domain, but there's actually a lot of out there. It's just maybe not as structured yet, and can be sourced. Okay, cool. Thanks, Alex, for a very nice talk. And yeah, hope to see you soon again. And
yes,
then thank you.
Enjoy the workshop. Thank you.
Thanks. And then we'll go to the next big point. Which is the challenges. So same as for the last two iterations of MaCVi, we had competitions, and very nicely motivated right now is one of the problems we always hear, for example, the Maritime robotics guys, when I talk to them, they always say, we don't have data. It's really hard for students to do something because you need access to water or a boat or whatever. So we want to, with these challenges, we want to kind of disentangle that a little bit and make it a little bit easier, this entry hurdle that students have usually. And the last years we had competitions on UAV and USV-based object detection, multi-object tracking, identification. We had some segmentation-based approaches. But this year, what's new is we have a USV-based object distance estimation challenge. So where the goal is to predict distances from a monocular camera to objects. We have pan-optic segmentation for the first time based on a data set that has been published at MaCVi, and also underwater image restoration. And yeah, the way we're gonna discuss the challenges, or let me give some background on how the challenges were done. So from roughly September 13th to December 19th, people had access to the data set, some starter code, and all that via our workshop webpage. And people could upload their predictions either in the form from predictions or neural network. They could upload it to our webpage, and then it would be compared against the ground truth. There were some limitations for the upload so that you can just randomly get to your goal. We received over 7, and track is featured in the challenge summary paper. If you haven't read it, I recommend going through that. And importantly, we have some sponsors that helped us make this a little bit more engaging. Maybe Shield AI sponsored prizes for the best teams of the distance estimation challenge. 2 GPUs. We're going to talk about that in a second. Luxana sponsored a prize for the best team in the embedded challenge. And Lookout captured the data set for this distance estimation challenge. And with that, I would hand it over to Martin, who's going to talk about the approximate supervised object distance estimation challenge. If you are here, Martin.
Yes, hi everybody. I hope you can hear me.
Yes, perfect. You
Very
want to
nice.
share?
Yes, I will go ahead and share my screen. Okay, can you see it?
Perfect, yeah.
Very well. Okay. So yeah, the first challenge this year, which I will now present, is the approximate supervised object distance estimation. The target of this challenge is to develop a object detection model, which is also capable of predicting the metric distance in meters, for example, for the detected object. So alongside the bounding box predictions, which you usually get by default object detectors, we also want the distance for each of the detected objects, which you can see here in the image on the right. So in our case, we focused on detecting buoys and maritime navigational aids like channel markers. And yeah, we predicted the distance for each of the detected objects. We also have the target or the goal to have a real-time capable system, so a real-time capable detection pipeline. And we want to be able to integrate the approaches, the developed approaches with state-of-the-art object detectors. So to also get a quite good performance on the image domain and on the object detection part. So not only a good distance estimate. So we want to combine both. And the motivation behind this challenge is that by avoiding to employ sensors which are directly capable of producing a distance value, for example, LiDAR or radar, which first of all are costly, but which also would need to be installed on the vessels. We can avoid to fuse the data. For example, for LiDAR, we would obtain point clouds, or for radar, we would get blobs. And this we would have to fuse with the images, so the information that's gathered from images, and that by directly predicting the distance in the images, so just relying on the image domain, we can avoid sensor fusion. And we want to have a good performance over different ranges. So we want to be able to maybe perform obstacle avoidance, which would mainly focus on objects that are relatively close to the vessel, but we also want to detect and predict distances that are much further away. And one common approach nowadays to get distance estimates or depth estimates is to use depth estimation networks, which produce a depth map over the entire image. However, we discovered that those approaches do not really work well for small and really distant objects like buoys, for example. So that's why we wanted to develop a new approach. So now let's look at the data set and the provided model, which we kind of provided to the challenge participants. So we created a data set comprising of roughly 5,000 labeled instances. And these instances consisted of bounding box coordinates, but also of the distance ground truth value to the objects, from the camera to the objects. And as I already said, we only have a single class prediction problem. So we only want to detect buoys, and only the buoys are labeled in our case. Overall, we extracted the frames from over 40 different videos. So we have quite a diverse range of settings, mainly in coastal areas and harbors, but also some in open waters and seas. And to do this, to create this data set, we developed a custom labeling tool which can establish the correspondence between the labeled bounding boxes and the chart markers. So basically, you could select the bounding boxes on the one hand and the chart markers on the other hand, and the hover sign distance was computed. And the result of that is depicted on the right side. So here you can see the kernel density estimate over our data set with reference to the distance, to the metric distance. And as you can see, we have quite a large range, I would say, of distances. So we start at maybe like 10 to 20 meters. Most of our samples are between 100 and 500 meters, but we also include samples even above 1,000 meters, so above 1 kilometer. And that's usually, these objects are really, really small in the image domain, so it may be hard to detect, but we want to kind of push the boundaries and see how good these models can get. And besides the dataset, we also provided an adapted model of the YOLO V7 architecture to kind of get a head start for our participants. And you can see the architecture depicted here. So YOLO V7 consists of a backbone, a neck, and a head. And what we did, we just adapted the heads, which operate on extracted feature maps. And each head predicts the bounding box offsets with reference to an anchor, but also object and class labels. And now what we did was, as you can see in the center below, is to extend this vector, the prediction vector, with the distance estimate. And in our case, the distance estimate is normalized, so we apply a sigmoid function, but it is later rescaled to meters by multiplying, for example, with the maximum distance to obtain the metric estimate, actually. Now let's have a look at our evaluation metrics. So since we have like kind of a combined problem, we want to predict the distance on the one hand and want to, of course, also measure the performance of the distance estimates. But we also need to check if the models are capable of predicting objects well enough, at least. So first of all, let's quickly discuss the distance estimates or the distance metrics. So we have, on the one hand, we have just the absolute error, where we compute the L1 error between the ground truth distance and the predicted distance. And then we also provide a relative distance error, which is extended by the normalized confidence. So basically, if there is a large distance error and the confidence for the predicted bounding box was also high, then this will have a larger impact on the relative error. And for the other case, if it was a smaller confidence, then the error will not be weighted as heavily. And to combine this with the object detection domain and object detection metrics, we produced this combined metric, which were actually, this metric was used to score the submitted models of the participants on our scoreboard. And as you can see, we multiply the AP50 to 95 metric with our relative distance error, which is subtracted from 1 to obtain a value which should be as high as possible. So if it's close to 1, it's a really good model. If it's close to 0, it's not so good, possibly. We also had some submission requirements. So first of all, the parameter count was limited to 50 million because, as I said, we wanted to have to some extent real-time capability, and also the models were evaluated on the MaCVi service. So that's why we had to make sure the inference time is not too large. We also required the models to be exported to ONNX so we can run arbitrary models on CPU and GPU. And NMS, non-max suppression, should not be included in the ONNX exports. And finally, what we also did was to rescale the images to 1024 times 1024 pixels. So the participants should make sure that their submitted models are optimized to these kind of rescaled images. Okay, now let's have a look at the results. So here you can see the baseline model and the two top scoring models which managed to improve the results over the baseline model. The first model is called Data Enhance, and it's it was developed at the Nanjing University of Science and Technology by Jiang Zhong, Zhe Zhang, Jiu Li, Zhuran Chen, and Yang Yang. And the second scoring model is called YOLO V7 Depth Widened, was developed at the University of Zagreb, specifically the Faculty of Engineering and Computing. And the developers are called Matej Fabianic and Fausto Ferreira. And as we can see, actually kind of interesting, I would say, the first scoring method really excels in the image domain. So it has really good results regarding the AP metrics, but also manages to outperform the baseline model in terms of the distance errors. And on the other hand, the second scoring model was slightly less capable of doing object detection, but still better than the baseline model. But it was really remarkably good, I would say, at the distance estimates. And that is depicted here. So here you can see the comparison over the baseline model and the two top scoring approaches. And what you can see is that for small distances, for example, 0 between 200 meters, we have really, really low distance errors. So below 20 meters even on average. And even for larger distances, for example, 400 to 600 meters, we still have distance errors between roughly 60 meters. And that's, I would say, that's quite low. And you can definitely work with that and build maybe other models or algorithms on top of that, which require a distance estimate for the detected objects. And similar results are depicted on the right-hand side, where here you can see the distributions over the different distance bins. And as you can see, maybe it's interesting to note that for larger distances, the prediction is usually lower than the ground truth. So the model predicts a lower distance, which might be attributed to the fact that most of our samples are in the distance bin 400 to 600 meters and 200 to 400 meters. So objects that are farther away, so for example, 600 to 1000 meters, that's why the model might be skewed to predict closer distances. All right, so that covers the approximate supervised object distance estimation challenge. And with that, I will hand over to the next presenter covering the segmentation-based challenges. Thank you, everybody.
Thank you, Martin. If there's one quick question, then please. Otherwise, we'll go over to the next competition. We'll hear from the challenge winners of this competition after presenting all the challenges. Okay, cool. Then I guess we can go on to the next USV-based segmentation challenge.
Okay. Hello, can you hear me okay?
Yes, perfect.
Okay. Hello, everyone. My name is Jon Muchovic, and I was overseeing the USV Semantic Segmentation Challenge for this year. Now, this year we had 3 purely image-based USV scene parsing challenges, namely the USV-based optical segmentation, the USV-based embedded optical segmentation, and the USV-based panoptic segmentation. Now, the dataset for all the 3 challenges is called LARS, and all the 3 challenges were evaluated on it. So LARS is a panoptic maritime dataset that was produced by our colleague Loise Just. It's a diverse dataset made up of more than 4,000 panoptically labeled images. You can see that at the right of the screen. It contains diverse scenarios with regard to the various visual conditions and obstacle types. And you can see the visual conditions such as fog or nighttime or sun glare or things like that here in the left side of the slide. Now the goal of the obstacle segmentation challenge was basically just to separate the image pixels into 3 classes. Namely, these are water and sky, which are fairly self-explanatory, and obstacle. And that essentially means everything else, which includes the shore, piers, boats, and whatever other floating obstacles that we managed to find in the annotated scenes. Now the challenge submissions were the predicted segmentation masks on the Lars test dataset. The metrics were first the classical MIOU score, so the intersection over union averaged over all 3 classes. And now, given that the Lars dataset is panoptically annotated, we were also able to calculate obstacle level performance metrics in terms of true positive, false positives, and false negatives, which allowed us to calculate the F1 score. And then the final metric named Q was just a product of the MIOU and the F1 scores. Now, this year we received 59 submissions from 16 different teams. But as it turns out, only the top 3 submissions performed better than the last year's best performing methods. So here on the slide, you can see in gray the last year's top 3 methods, and on the top are the 3 from this year. Now, 2 of the top 3 performing methods here were based on mask-2 former, and the last one was based on Keynote. All of the top performing methods quite decidedly outperformed last year's top performers. Here we can observe that the IOU overall is pretty high, as it also was last year, hinting that likely most of the pixels are segmented correctly for the large part. And the somewhat lower F1 scores kind of shows that the main difference in performance stems from the method's ability to detect the very small obstacles. So when we analyze the results, we can see that the top 3 methods display robustness to various difficult visual conditions, and also they present the ability to detect very small distant objects. The first place method, waterformer, performed the best overall because it's the first one, but the analysis of different visual attributes also shows that the second place, WS former, performed somewhat better under some difficult visual conditions like underexposure, sun glitter, and fog, as you can see here on the graphs. So, not to be too long, here are the winning teams for this challenge. The first place goes to the GIST AI lab with the waterformer method. The second goes to a multi-institution team with the WS former method, and the third goes to an independent researcher with the advanced KNet method. I would like to congratulate again the winning teams, and now pass the presentation forward to Mattia.
Thank you, John.
Would it be possible for you to share your?
What do you mean, my presentation?
Yeah, the slides going forward.
Yeah, you just need to tell me when to switch, but yeah, I can do that for you. Just give me a sec. Here we go.
Yeah, thanks. Okay, hey everyone, I'm Mattia from Luxonis, and I'll present the Embedded Obstacle Segmentation Challenge that we hosted this year. So the Embedded Obstacle Segmentation Challenge was an extension of the classical obstacle segmentation challenge that Jon presented. So it has the same goal to segment the input image into water, obstacles, and sky components. As additional constraint, we require that methods must be suitable for deployment on embedded devices. And as an embedded devices, we chose our WACV, which is a next-gen device that you can already pre-order, and it contains Qualcomm QCS 8550 chip, which is capable of 48 TOPS int8 performance. So from evaluation perspective, we use the same metric Q, and then we require that methods are faster than 30 frames per second on an WACV, which we evaluated on a remote server. To kind of limit this challenge a bit more, we introduced additional requirements. For example, images had to have a fixed input shape, and they needed to be ImageNet preprocessed. We required all methods to have a single output, which was argmax segmentation mask. And then all of the methods had to have a static graph and had to adhere to a set of supported operations so that they were possible to export to Onyx, which we then accepted on our evaluation server. Overall, we received 26 submissions from 4 different teams, and we received multiple submissions per team. The winning methods focused on lightweight architectures, and all of the 2 winning methods outperformed the last year's winning method. As you can see here on the results, compared to obstacle segmentation challenge, the quality metric is quite a bit lower, and we believe this is mainly due to detection of the small obstacles or objects, as we'll see on the next slide. So yeah, looking at the images, so from the quality analysis, we can see that the winning method achieved improved performance on hard reflections. You can see this in the first and the second row. And the winning method also improved performance in challenging conditions, such as presence of plants or debris, and it's also visible from the second row. In the last row, you can see that all of the methods struggle with very small obstacles. Main reason for this is that we do require a fixed input shape. And so because of the downsizing, the methods can really attend to those obstacles. As a result, we're thinking of potentially relaxing the FPS constraints for the next year and allowing bigger input shapes on the images. And the winners, so the winners of the USV-based embedded obstacle segmentation challenge, the first place goes to Dalian Maritime University from School of Marine Engineering with RSOS-NET. And then the second place belongs to ACV Lab from National Cheng Kung University with Segawara Ensemble or EFF-NET. The first place will be awarded $500 Luxonis store voucher. Congratulations to all the winners.
Thank you, Matija. Quick question, otherwise we'll go to panoptic segmentation. All right. Loise, you can go ahead.
Hello, everyone. My name is Loise, and I will present the results for the USV-based panoptic segmentation challenge. So this is a new challenge that we introduced to MaCVi in this year. It's a slightly more difficult, or not slightly, but quite a bit more difficult challenge to the 2 challenges that my colleagues presented before me. So in addition to segmenting the image into the sky, obstacles, and water components, we also want to detect and segment individual instances of 8 different obstacle types, as we can see in these examples below. So the submission protocol that we used was as following. The participants were allowed to train their panoptic methods on the large training set, as well as other optional data sets that they found. And then they would submit their predictions on the test set to our evaluation server, which automatically evaluated the panoptic quality of the predictions. So this is a standard panoptic metric that is used in other tasks. And in addition to this, we also report the quality separately on the thing and the stuff classes. So the challenge received in total 21 submissions from 7 different teams. In addition, we also contributed our new method called Panzer to the leaderboards during the challenge, which achieves state-of-the-art performance on this task, but it was not included in the considerations for the challenge standings. We are happy to report that all of the teams that submitted this year significantly outperformed the baseline that we provided. And specifically, the winning method did so by 12.5 points increase in PQ compared to the baseline. Also, the second placing team was not far behind from the first place, with only 0.9 panoptic quality decrease. So in order to kind of understand the differences between these methods a bit better, we show here the detection performance of the top 3 methods with respect to the size of the obstacles that we're detecting. And we can see that the main difference between the first and the second method is the ability to detect very small obstacles. So these are obstacles that have the diagonal of between 0 and 16 pixels in the image. And in this case, the first placing MaCVi method significantly outperforms the competition. This can also be observed in some qualitative examples. So here in this very dense and difficult scene with many small objects, the top performing methods like MaCVi or our Panzer method are able to detect a much higher number of instances of these boats compared to the second placing method, which doesn't predict instances on all of the methods, on all of the obstacles, but still produces the correct segmentation masks, or the third placing method, which in this case fails to get some instances for some of these obstacles. Overall, these kind of dense scenes are still like one of the biggest challenges in this benchmark, and there's still a lot of potential to improve this moving forward. So to conclude, I'd like to announce the winners of the Panoptic Segmentation Challenge. In the third place, we have Josip Šarić from the University of Ljubljana with his method FC Clip Lars. Then in the second place, we have Seonju Lee, Yeonshuk Lee, and Kyobin Lee from the Gwangju Institute of Science and Technology with the method Panoptic Waterformer. And in the first place, we have Yannick Sheikh, Andreas Michel, Wolfgang Gross, and Martin Weinmann from Fraunhofer IOSB with their method MaCVi. I'd like to congratulate all the winners and also thank all other participating teams for participating in this challenge. The teams that are presented here will also present their winning methods in the next section, so stay tuned for that. And with that, I'd like to pass over to our final challenge of this year.
Thanks, Loisa. Any short question, otherwise we go Chaitra or Uma? Who's gonna present?
Yeah. Can you share the presentation from the deck? Benjamin?
Okay, I can do it also.
Yeah.
Can you see that?
Yeah, thank you. So this is the new addition in MaCVi workshop this time. So we are introducing a new challenge, particularly for underwater vision. So marine vision restoration challenge. The underwater environment actually presents more challenges, which are also unique to the underwater scenarios, with poor visibility, color distortion, and light scattering, which also hinders the accurate species detection, any object detection environment. Typical traditional image formation models do not capture the physics happening in the underwater image restoration, underwater image formation, which is happening. So what we have done is, next slide, please. So here what we have done is we propose the physics aware image formation model, where in the direct scattering part, only the line of sight distance is assumed to be a function. So here we introduce the downwelling depth, which is d, also as a part of a direct scattering phenomena. And then we used this revised image formation model to generate a synthetic data, and we achieved a very tangible results, outperforming the state of the art methods. And this is a part of the ACM transaction on multimedia, and we use the same idea to generate a data set for the present challenge. Next. So here, as I said, we use the similar data, whatever proposed in RSU IGM, and we gave 6,000 images, which has a particular characteristics of all the different types of underwater scenarios, both ocean beds as well as the coastal bed, as per the Jarlow water types. With varying depth. So there are Jarlow water type classifies these 5 different types for ocean and 5 different types for coastal bed, with a varying depth from 1 meter to 20 meter. So each scene in the data set has one ground truth and corresponding these 200 different class of images covering the entire the underwater space. So this is the ground truth. And next, the quality metric used here, both perceptual quality as well as the object detection quality metric. So the first few 3 are the for the quality metric, which is quantitative metric, which define the color distortion, clarity of underwater images, as well as the contrast and the fog density. Together, all the 3 of them together define these parameters. And the next 3, the MIO, F1 score, and MAP, defined for the object detection. We define the combined metric for the object detection context. And these are the next slide, please. Like, there were 45 plus submissions from 7 teams, and all submitted submissions outperformed the baseline. And these are the parameters for the top 4 teams, and they outperformed. And the first team is actually performing better in all. The first and second team, there is the first UIChem is a difference. Otherwise, there is a mix of few metrics based on the combined metric. The first team outperforms the second team, and the winners for this challenge are, so next. So first is the Nanjing University of Science and Technology, and the team consists of Epenglin, Zhang Yang, Nanjiang, and Yang Yang. And the second team is Beijing University of Post and Telecommunication, Beijing, and the team consists of Yutang Liu and Fifeng. And the third team is a Michigan Technological University. The team members are Ali Awad, Ivan Lucas, and Ashraf Salim. And the fourth team is ACV Lab, National Cheng Kung University. The team members are Ching Heng Cheng, Yu Fan Lin, and Tol Yu Lin, and Ching Chung Su. And I congratulate all the winners, and actually I thank all the participants and present in the challenge. And I also thank the entire team for this wonderful collaborative work.
Thanks, Uma.
Thank you.
That's a quick question. Otherwise, we're gonna go to the last part of before the break, which is gonna be the challenge winner presentations. And the way this is gonna play out is according to the schedule. So we're gonna go over the approximate supervised object distance estimation challenge, like the same order essentially as we just saw. And so first speaker is going to discuss his method on the approximate supervised distance estimation, namely YOLO V7 depth widened. Mate, you want to come here? So you can share a presentation with me?
Maybe I sent something, maybe I didn't.
I think that makes it easier then. No, but
Sorry now.
maybe.
No, Microsoft is blocking me in the US. I can't even log in for.
Well, actually, you can go into Zoom and share from there, and then the audio setup is going to be the same.
Yeah, the Zoom.
Can you go into Zoom? It's in the Excel sheet you have there, it's not program.
No, because I can't open Outlook.
You can go on MaCVi. Go on MaCVi. Right, and then open the program. And here. And then click on the Zoom link. Like copy it. If you have Zoom on there, I guess you can also do it in the browser. Hopefully. You can join from browser instead. Yeah. Should be good enough. Never allow. Just you don't care about camera. Well, actually, you care about sharing. Make it loud. And then share screen. Entire screen.
Okay, so hi everyone. I'm Mate. I'm from the Faculty of Electrical Engineering and Computing from Zagreb in Croatia. And together with my mentor, Fausto Ferreira, we took the second place in the approximate supervised object distance estimation challenge. Okay, so without going into challenge overview, first, yeah, we used the provided starter code, which is a modified YOLO V7 with the distance estimation head. And before trying that, I just want to say that we tried using some existing distance estimation software to see how it works on outdoor pictures in maritime environments. We tried depth anything version 2, and we saw that right around when the challenge was ending, there's a new paper called Prompt Depth Anything 4K, which is a metric depth estimation model. So with depth anything, you kind of get good results. You get good results, but it's not metric results. So this is just relative. Like the model knows that the boat is in front of the island and the sky is behind the island and so on, but there's no metric depth going on there. And this was the new model. I just put this here to
to show what's possible. But as I said, this came out just when the challenge was ending. But it's like really cool technology because with just a simple iPhone LiDAR, they get results like these, which is, to me, it's insane that you can get this with just a mobile phone. We also tried using Depth Pro, which came out from Apple. But again, it doesn't work for outdoors. So it's really good indoors, close-ups, and so on. But once the distances are more than 20, 30, 40 meters, it's not really working good. And yeah, so these were the results. You already saw this. We had problems with the bounding boxes, basically because YOLO model, like it initially struggles with small bounding boxes, and then the model also has to do depth estimation, which makes the problem of small bounding boxes even worse. We tried to correct this. Let's see if I have it here. Yeah, so we tried to correct this by doubling the loss for objects that are close, so that at least we have good results for close objects. And we played around with the scale parameter, which is a hyperparameter during training, so that the pictures get zoomed in a little bit in order to try to get the bounding boxes a bit more detailed. And yeah, I guess that's it. And we used 49 million parameters in width, since the limit was 50 million. And yeah, why did we use 441? Because when looking at the training data set, it looked like a good cutoff point. Like most of the buoys and sea markers were below 440 meters. In the test data set, which was not available to us before the challenge ended, yeah, it doesn't make a lot of sense, but that's okay. And yeah, and I don't know if this was shown. So basically, the further away the objects are, there's more distance error. The closer they are, there's less. And yeah, that's basically it's just okay. Thank you.
I just want to mention real quick, also for Zoom, to prove. So the second place for the distance estimation challenge is going to be this one. That's going to be 4070 Ti, for which you're going to get, and you can also get a certificate sponsored by Shield AI, obviously. Awesome.
Thank you.
Okay, let me share again. So that was the second place. The first place, unfortunately, can't be with us. They have a video, but for time reasons, I'm choosing not to play the video, but we're going to upload all the videos to the webpage, and you can watch it later if you want. For reference, they won this one, the 4080, but we'll have to see how we can send it to them. It's in China, but we find a way around the export restrictions, maybe. AliExpress. Maybe, yeah. Okay. Okay, with that, we go to the next challenge, which is going to be the obstacle segmentation challenge. So same reason, for time reasons, I'm not going to show the video for Himanshu Kumar, unless you're here in person, like virtually or in person. then you can present. But otherwise, I should say video we can watch online later. I don't see any complaints. All right. So, but then we go to the first place of the USV-based obstacle segmentation challenge, water former, and Theong Lee is here in person. And I do have your presentation, I think. So you can just show it from here.
Hello, I'm Sungju Lee from AI Artificial Intelligence Lab in JIS at South Korea. We got first prize in USV-based obstacle segmentation challenge. Our method named waterformer. In waterformer, we used vision foundation model. Vision foundation model is a large AI model pre-trained with large-scale image data sets, and due to VFM's outstanding imaging capabilities, it is widely used in vision tests, such as for semantic segmentation. So there are many vision foundation models, and in this test, we use Dino version 2. We use the Dino version 2, which is demonstrate exceptional performance in many visual recognition tasks. It is trained on a billion-scale data set named LVD, and it shows robust feature learning in many tasks. But a VPM mainly have a lot of training parameters. So we use parameter efficient fine-tuning methods, which is used for additional model or parameter during training, and the other vision foundation blocks are frozen. And the other key idea is using deformable convolution. So we noticed that the vision foundation models are mainly are transformer architectures, and transformer architectures is has a lack of local spatial features. So we integrate the deformable convolution into the adapter to efficiently fine-tuning the vision foundation model. So it is a detailed architectural adapter. Our method is based on adaptomer, which is a bottleneck structure, and adapter structure. It has a down NLP and non-linear activation layer and deformable convolution layer. And after that, we use up NLP to fit the feature dimension. So the refined feature is multiplied by a scaling factor alpha, and the refined feature is added to the output of vision foundation at the block of vision foundation model. And we also a simple modification to improve the performance. To enhance the discrimination between water and dynamic obstacles, we separate the obstacle classes into static obstacles and dynamic obstacles during training. So as a result, we got performance improvement about 1.0 percent point in quality. During training, we use only large data set, and we also have a comparison on general domain generalization based semantic segmentation method and other challenging competitors method, and we have We have outperformed the other competitors' method, and simultaneously we outperformed the domain generalized segmentation method in other published in other conference. We also have some observation studies on bottleneck dimension and backbone capacity. For the bottleneck dimension, the bottleneck dimension size with 128 is optimal, and with the backbone capacity, the giant size is not optimal, and we found that the large size is optimal. So this highlights the importance of balancing model capacity and performance. Here's the qualitative results on other scenes, and we compared the other domain DGSS based method, and we shows better qualitative results on water surface, which have hard reflection. This is a reference, and thank you for listening.
Thank you. Yes, please.
A very short question. You introduced dynamic obstacles, but Mars doesn't have them on the page. Did you integrate them by yourself?
The question was for the people in Zoom, like, how did you get the dynamic obstacles? Did you label them, or yeah?
We use labels from Panoptic annotation, Panoptic segmentation annotation.
Sneaky, but valid. So, props to you. Okay. And then, yeah, so same reason, because of time, I'm not going to show videos of the two embedded obstacle segmentation approaches. If you're here in person or virtually, feel free to talk now. But otherwise, I'm going to upload the videos and you can watch them later. And instead, we're going to go to the third place of the USV-based panoptic segmentation challenge. If you're here, use it.
Hi, I'm on Zoom.
Perfect. You want to share your screen?
Yes. You can see it?
Yes. Perfect.
Yeah, okay, then I can start, right?
What's that? You want to start?
I can start, yes.
Yes, please.
Okay. So, hi everyone, in person and on Zoom. My name is Josip. I'm from University of Ljubljana, and today I'll tell you something about open vocabulary panoptic segmentation of maritime images. So this field of open vocabulary panoptic segmentation experiences like accelerated development since the introduction of visual language models such as CLIP. So with open vocabulary panoptic segmentation, we can basically segment an arbitrary object without that object being present in the training set. This is enabled by the joint vision language aligned feature space from visual language models, where we can classify some visual clues by embedding them into this shared space, and then comparing these visual embeddings with the textual embeddings of the classes of interest or classes of our data sets. So this ability is natural for CLIP, but various extensions are necessary to achieve dense open vocabulary prediction, such as semantic or panoptic segmentation. So one such extension is given by a model called FC-CLIP, which replaces the classical classifier in MaSK2 former with a language-based classifier. And I've used that model in my experiments. So typically, these models are trained on large-scale, densely labeled data sets with rich taxonomies such as COCO. And COCO collects like common scenes, And in my short research, I was interested, how do these models generalize on the maritime domain? So my first experiment was to take a FC clip model that is trained on COCO and that integrates a convex-based clip backbone and evaluate it on Lars validation set as is. And this model achieved poor results, like 18.2 panoptic quality and around 50 points mean intersection over union. And I was looking into possible reasons and noticed by visual inspection that static obstacles are not segmented at all in most of the images. And then I noticed that for these models, these text descriptions of classes are really important, and that without further context, static obstacle doesn't mean a lot to my model that was pre-trained on COCO. So my first attempt was to extend this vocabulary of classes, of text descriptions, by introducing additional class names for every class, and these names were synonyms or hyponyms. So for example, for static obstacle, I would add names like building, terrain, vegetation, rocks, shore, and others. And just by adding these names in class descriptions, the performance increased significantly to 27.6 panoptic quality points and 91.6 intersection over union points. But still, we have some issues, and one example is that this person on the rowboat is not segmented at all. And this is due to the misalignment between the labeling policy of the training dataset, COCO, and the labeling policy of the testing dataset, Lars. In Lars, this person is meant to be segmented as part of this rowboat. But on COCO, persons are segmented as individual instances. So there is really no easy way to kind of get around this mislabeling issue. So then I tried to fine-tune my model using the Lars training set, and then this led to a further increase in the performance. On validation set, I achieved 53.6 panoptic quality points and around 95 mean IO points. And then we can notice that this person is now segmented as part of the rowboat. So by training on such data set, we don't have the misalignment between the training and testing labeling policies. And the same model achieved 49.7 panoptic quality on the test set, which was enough for the third place on this year's challenge. And to conclude, I would like to state that I showed that zero-shot evaluation of these open vocabulary models on maritime scenes struggles due to the domain shift, taxonomy misalignment, and vague class names. We can address this by fine-tuning, but due to the overfitting, we risk that our model might lose the open vocabulary generalization ability. And in the future work, I would like to address this to see how we can fine-tune these models and still keep this ability to segment arbitrary objects that are possibly outside of our training taxonomy. Yeah, that's all from me. Thanks.
Thank you, David. Congratulations. Is there a quick question? No Zoom, also not. All right, thank you.
Thank you.
Then we're gonna go to the second place of the USV-based panoptic segmentation panoptic water former. We have you again, Jingyu. It's the same slide deck, right? This one, right? Am I sharing the screen? I'm sharing the screen. Yeah. Okay.
Oh, nice to see you again. My name is Song Lee, and I got second prize in USB-based panoptic segmentation challenge. I'm gonna shortly present my method, my key ideas, combining the waterform I presented before and well-performed instance segmentation model. Panoptic segmentation is a combination of symmetric segmentation and instance segmentation. And waterform is a powerful model for segmenting soft and thin class. And I also tried waterformer because panoptic segmentation because waterformer is based on mask to former, which can be trained in a panoptic manner, but it shows some worse performance. So I use some simple approach in this method. So first I segment the image into 4 classes, into soft, water, sky, and obstacle, and dynamic obstacle classes, which is class agnostic segmentation, and to instantiation the thin mask from waterformer. We employ well-performing instance segmentation. We use cascade mask RCNN and with internal image large size platform. Internal image is a kind of vision foundation model, hierarchical vision foundation model. So it can be well performed in instance segmentation, I think. So after that, I merged the instances using the instance bounding box and the semantic mask by intersection of union. So the final panoptic segmentation map can be resulted as follows. So to train the mask of thin class, the instance annotation is created from the panoptic annotation, except the sub classes. So for better training, we employed the couple pre-trained weights for the initialization of instance segmentation model. And for augmentation, we used a large scale training is used. And the other training details is included in the workshop paper. So to merge and assigning the thin mask, we first filter the instance mask with score threshold 0.5, which ensure the object score, and we sort the instance mask from a large to small area to ease or minimize the occlusion by large masks in a later step. Then I assign the label and instance information in some semantic segmentation map by the intersection of union. So IOE between the thin mask in semantic segmentation map and instance segmentation bounding box from instance segmentation map is used. I also tried the instance mask, but it performs worse than that we used instance bounding box. And the other unassigned mask we used, we fill the unassigned thin mask into static obstacle classes. So it is a simple presentation of our method. This is a reference, and thank you for listening.
Yep. All right. Quick question for you. Let's check Zoom, but nothing. All right. Thank you. Thank you very much. And then there's the first place, perfect for the panoptic segmentation challenge. I'm going to open up the slides. Should be good. All right.
Hello, everyone. My name is Yannick Schalk. I'm from the German Research Institute Fraunhofer, and I present to you the solution of the Panoptic Segmentation Challenge. So we used the Mass Dino model, which is built upon the Detectron-2 framework, so easy to train on new data sets. We used a pre-trained version of Mass Dino that was written on Coco with a SwimL backbone. That would also treat it on ImageNet 21K, and then we basically fine-tuned on LAS. So this Mass Dino, Dino is basically built on, Mass Dino is built on Dino. This is detection transformer model. Detection transformer model using a quite simple method, or constructed of like a backbone and then a transformer encoder and decoder structure. So an input image is fed to the backbone. In our case, it's SwimL. Then together with positional embeddings fed into the encoder to basically enhance features and then generate the initial contents and anchors for the decoder. In the decoder, we have, among other things, deformable attention. The important part here is so the red lines are basically the segmentation branch that are added to Dino. And here the pixel embedding map is an important part. Basically, the idea is from Mass Performer to use the information from the backbone and from the encoder to generate this pixel embedding map to be able to produce masks in that setting. Here are our quantitative results. So the bold ones are ours. Mass Dino achieves a p-value of 53.9. If we look at the second and third column, we see a significant drop between the things and stuff categories. And you can see the formula up in the top. And since the PQ is basically segmentation quality times the recognition quality, and our segmentation quality is already quite good. We try to improve that by basically just adding a VLM afterwards and try to see if the VLM matches the prediction of Mass Dino. So we fed our image with the prediction, so the bounding box information and the predicted class. What you also can see is the performance didn't improve, and we only could test some versions because the FPS in that past setting was quite low, and we just focused on the bold category to see if we can improve that. Again, it didn't improve, but the results or the testing showed some interesting research ideas, and we are following up on that. Yeah, also some qualitative results. So you can see, as previously mentioned, that also we see quite far distance objects are segmented and mostly with the correct label here on the top image. If you look on the next slide, you can also see that there is like some misclassification in the bottom row. There is like a duck labeled as a buoy instead of an animal. Yeah, thank you for your attention. If you have any questions, please do so.
Any question? Okay, so this concludes the Panoptic Segmentation Challenge. So, Loisa, are you still here?
Yeah, I'm here.
Okay, so this next short talk, Loisa, if you can make it short, it's going to be the method that you already teasered, which they looked at during the challenge, but was not counted in the challenge, but it might be interesting for you to consider as a method. So, Loisa, you want to share your screen?
Yeah, thank you, Benjamin. So yeah, I'll just briefly present our Pensor method, which is a new state-of-the-art method for the Lars benchmark. So the way we approach developing this method is we first looked at the main issues of existing approaches, such as mask-to-former and mask-dino. And we saw that like one of the big problems is that this method tends to group different instances as a single instance. And this also leads to clashes during the post-processing, and many of objects disappear from predictions as a result. The second problem is what we call query drift. So this is when we start with perfectly good proposals with bounding boxes correctly positioned to the objects. And then sometimes during the decoding process, these queries drift away even when no alternative proposals exist. To address these issues, we introduce a new network we call Panzer. It's a novel panoptic segmentation network, and it's roughly based on mask transformer architectures like MaskDyno or Mask2Former, but we take several key changes to this paradigm. So first, to address the problem of instance separation, we utilize the predicted bounding boxes as a way to limit the segmentation mask to a local area around the object. And this is only done for the think classes. And then secondly, to address the query drift, we rethink the way the ground truth is matched during the training. So in a traditional Hungarian matching, only one prediction is matched with each ground truth segment. But when we use proposals, this is not ideal and can lead to this query drift. So instead, we allow multiple proposals to match to the same ground truth segment. And in this way, we prevent the network to learn this query drift behavior during training. We also improve several other key components of the network. So we redesign the proposal generation so that it focuses more on the detection of small objects. And we also separate the handling of thing and stuff classes. Specifically, we use learnable queries for the stuff classes and proposals for thing classes. We report the results on the Lars benchmark, and we observe that Panzer consistently outperforms the previous state of the art, which is MaskDyno, on all obstacle sizes. And interestingly, even when we use a simpler ResNet 50 backbone, Panzer is still able to outperform MaskDyno when it uses a more complex SwinL backbone. And finally, for some visual results, we can see that Panzer effectively solves this problem of merging of instances that is shown on the left side. And this also leads to more detection on crowded scenes and less common occurrences of empty predictions, as is shown on the right side of the images. Yeah, that's it from my side. Thank you for your attention. And if you're interested in learning more about our method, you're welcome to read our preliminary paper on arXiv.
All right, thanks, Loise. Is there any question for Loise in Zoom chat or here? Otherwise, it doesn't seem like it. Thanks, Loise, again. And then we go to the last petition, which is going to be the Marine Vision Restoration Challenge. We're going to have one talk only, the third place. The others are videos again, and for time reasons, I'm going to upload them. But Ali, are you here? What do I have from you?
It's a presentation PDF.
Did you send it to me?
Your menu, right?
Yes. Did you send it here?
Yes.
This one?
Me in the email. Yeah.
It's a poster, but you want to? Okay.
Okay.
No, that's all right. It's Thunderbird. So let me do this. I'll download it and then open it as PDF properly. And we can do this download. Let's just do it.
Hello, everyone. This is Alahi from Michigan Technological University. We won the third position in the Marine Vision Restoration Challenge. And we have some interesting results to share with you today. So basically, the problem is underwater images, as you all know, suffer from severe degradation. And they have low contrast, low color quality, and they suffer from color casts. And this affects the object detection performance as well. So what we first did is we started by enhancing the images using different image enhancement algorithms. Yeah, I can use this. I think this is better. Enhancing the images using different image enhancement algorithms and evaluating the performance before and after image enhancement. And to our surprise, we got lower performance after enhancement in comparison to the originals. Lower or equal, meaning that image enhancement is actually either deteriorating the object detection performance or not doing anything at all in terms of detection. For this reason, we wanted to go through a more thorough evaluation. So we visually inspected the images, and we found out that there are some images where image enhancement actually perform better. For example, this first one, it was enhanced by this algorithm over here. And in the ground truth images, in the original images, the diver here was not detected. But with the enhanced version, the diver here was detected. So although enhancement in general has a negative effect, overall negative effect on detection, there are some images that actually enhances detection. And for this reason, we mixed original and enhanced images to come up with a new data set containing enhanced images and original images that perform better than both the original images and the enhanced images. That was one of the main observations through our research. And the other observation is that during our visual inspections of the images, we also found out that there are a lot of images that contain mislabeled objects, meaning human annotators did not annotate those objects properly, or they missed them because the images are of very low quality and they have very severe color casts, such as this one over here. And when we looked at the enhanced version of the images, we found out there are so many objects that are not annotated. And unfortunately, when the detector actually detects a correct object, it will be a false positive because it's not in the ground truth. And for this reason, we actually re-annotated, revised the annotation of one of the largest publicly available data sets for underwater images. And on average, we got an increase of 9 bounding boxes per image. That's an increase that was not in the ground truth. So that was shocking for us. And when we evaluated the original ground truth versus the revised version, the original ground truth was only able to achieve a mean average precision of 51%, which is very, I mean, this is the ground truth. It should be 100%. And so basically, the models here were trained using the original annotations, but tested once with the original annotations and once with the revised annotations. And we did not find any MAP difference because the models were not trained on the original annotation. And as a conclusion from this, current data sets should be revised and enhancement should be used as the first step before doing even image labeling for human annotators to see those objects that are hidden and that enhancement are making them more visible. This is number one. And number two, we encourage researchers to develop ways to predict when to enhance images and when to leave them as in the original shape to get a better object detection performance. Thank you.
That's valuable feedback for sure. Awesome. Is there a quick question on that? Is that? I mean, it's an answer.
How do you mix this? Oh, that's a good question.
The question is, how do you mix the images?
Yes, because this was only a proof of concept, because in the literature, enhancement always degrades the object detection. So we wanted to prove that actually enhancement has the capability to increase the detection performance. So actually we mix the images based on their object detection. So now we are trying to train a model to predict when to enhance the image by when to leave it as it is.
But technically, how do you take images and you mix them averaging pixel values?
I'm sorry?
How do you do technical in mix images? You average pixel values.
So you have the original data set, and then it has a version of that original data set. Some images here perform better, and some images here perform better. You get the images that are performing better from here, and the images that are performing better from here, and you have new data.
So it's a fail. Or
no, you get that.
You mix them in a single image.
No, not in the single image. You get the best performing one, either enhanced or original, and you will get a new data set with the same number of images, but it has enhanced version and original. And now the question is, well, how do we predict when to enhance the image to get better object detection performance and when to leave? Why are those images? Why do they have better object detection performance and others do not? That's the question. And this is what we are actively working on. Basically, this is a research paper. It's on archive right now, and this is another one. It's on MDPI. I encourage you to read them to find more details. Another question? Do we have that for us?
I'd say we have break anyways, so maybe if you can discuss like right now, and I'm just gonna say, yeah, thank you. And summary, essentially is reach out to him and ask him the same question if you want. But yeah, let's go back to the program bridge real quick. So as I said, those two videos are gonna be uploaded. So this concludes this part, presentation of challenge winners. Just in time, actually, crazy. And we're gonna have a coffee break. It's gonna be quick. Maybe we extend it for a few minutes, but please come back at around 10:15. We're gonna have two keynotes, mostly gonna be on underwater computer vision, and we're gonna have the spotlight presentation of accepted papers. And yeah, see you in a bit.
I had a question because thank you.
Yeah, hi. This is Rajagopalan, Professor Benjamin. Can you hear me?
Give me 1 second. Yes.
No problem. Yeah, just wanted to check with you when I need to set things up.
Okay, yeah, should be good. Let me give me 1 minute and then
no problem. No problem.
Yeah. Hi, Raju. This is Uma.
Hi, Uma.
Hi.
All good till now.
Yeah. It was good so far.
Professor Rajagopalan, are you? Is
Yes, I am
everything
here.
settled?
Yeah,
You
I'm
still
here.
have. I just wanted to ask if anything is good.
Yeah, I guess so, man. I just wanted to see if the video and stuff is coming out okay. Can I turn my camera on at this time or want me to wait?
So we're gonna wait a few minutes, but if you want to test something, you can.
Yeah, I just thought maybe I'll flash my slide and then we just see whether the screen is presenting okay.
Yeah, sounds good.
All right, so let me first turn on the camera so that people can see me. Am I visible?
Yes.
Yes, very much.
Now let me go for screen sharing. Right. And yeah.
Yeah.
And there's the
Yeah.
slideshow. Are you able to see
Good,
my
good.
slide now?
Yeah, we can. We are able to.
No problem.
Yeah.
Very good. Then I guess we are all set then. And I'm also audible, right? There's no problem with the audio.
No, it's clear. Audio is clear. How
Okay,
about
great.
there, Benjamin? Its audio
Yeah.
is clear.
We can
Okay.
hear and see everything perfectly. So yeah.
Yeah.
But let's give it like 3 more minutes, just because people
Yes.
want to click in here, and then we'll be ready in a few minutes.
Great,
Cool.
great. I'll be back then, right? 3 minutes.
Perfect. All right, let's go on to the next point. Let me share my screen really shortly to announce the next point. point. For me, for the introduction. All right, so the next point is going to be a keynote by Professor Dr. Rajagopalan. And yeah, I don't know, Uma, do you want to introduce?
Yeah, I'll introduce. Hello, good morning. Welcome to the second keynote session of this workshop. So we are happy to have Dr. A.N. Rajagopalan from IIT Madras. Thank you very much for accepting and to be sharing your some of your work here, Raju. So very brief intro. Dr. A.N. Rajagopalan received the PhD degree from electrical engineering from IIT Bombay during 1998. He was a visiting scientist at Image Communication Lab, University of Erlangen, Germany. He was with the Center of Automation Research, University of Maryland from 98 to 2000 as a research faculty before joining Department of Electrical Engineering, IIT Madras, where he currently serves as a Starlight Technology Chair Professor. His research interests include deep learning, image restoration for deblurring, super resolution in painting and dehazing, 3D recovery, underwater imaging, multimodal learning, and image forensics. He's a fellow of Alexander Humboldt Foundation, Germany, a fellow of Indian National Academy of Engineering, and a fellow of Asia Pacific Artificial Intelligence Association. He served as associate editor of TPAMI from 2007 to 2011, associate editor of TIP from 12 to 16, and a senior area editor of IEEE transaction on image processing from 16 to 24. He was the area chair at ICPR 24, CVPR 22, ACCV 22. He is a recipient of DAE SRC Outstanding Investigator Award in 2012, WACV Award in 2013, Mid-Career Research and Development Award from IIT Madras in 2014, Google India AML Research Award for Faculty in 2018, and Qualcomm Faculty Award in 2022. He is a co-author of two books, a well-known Depth from Defocus, and I've been associated with Raj and know Raj from 1997. So welcome, Raj, again. Over to you.
Thank you so much, Uma. And I think that was not really a brief intro. Maybe we should have made it shorter. But anyway, thank you so much. And thanks to all the thanks to the organizers, for this opportunity. And good morning to all of you. Let me share my screen, right? And let me start my talk. Uma, I think you may want to. Okay.
Anything?
No, I was just wondering whether my screen is coming up, or has it come up?
Yeah.
Yes.
Yes.
Okay.
Yeah. It's...
All right. So let me just put it in slideshow. All
Yeah.
right. Okay. Now let me minimize this. All right. So I thought, right in this talk, I'm going to be talking about enabling visual understanding of this one, underwater scenes. And there's a work done by my PhD students, Nisha Varghese and Ashish Kumar. And there's also a project that was sponsored by this one, DST India. And I, of course, acknowledge the support from the organization. Let me just start by saying that when we talk about underwater vision research, I mean, we are faced with challenges of several kinds. Like, for example, we know that there is absorption, there is scattering, which kind of leads to a distortion of the color, low contrast, blurriness, and kind of things like that. Then, of course, we have also lighting conditions that could be non-uniform. Then you could have suspended particles. Then there is also a scarcity, right, in terms of what you can acquire underwater. It's not like what you can do right in air, right? As opposed to that, even acquiring underwater data is not easy, and therefore, right, that also is a kind of a separate dimension in terms of what you can do with underwater images. And then in terms of the ground truth, right, that is also very hard. I mean, even if you take a LiDAR down, it's not really as good as what you get outside. And of course, it's not anyway a cheap option. And we are looking at vision-based kind of research. And therefore, right, even having ground truth, the depth predictions or the ground truth image data is not easy. There's also a big domain gap, in terms of the methods, right, that we typically build for in-air images. They don't, I mean, if you directly apply them to underwater images, they kind of seldom do well. And the last thing, right, that I also wanted to mention was that we want something which works in real time. I mean, as far as we can, right, we would like to have a method which is actually real time. So by kind of enhanced visual understanding, what I mean is, I mean, there are so many downstream tasks, which require an image which is of a high quality. And because of the fact that underwater images typically suffer from all kinds of things, low contrast and all that, blurring included, and low light and all of that. And therefore, what typically happens is that if you try to do tasks like segmentation, salient point detection, edge detection, and key point detection and things like that, then you kind of typically can show that what you get as output, right, from these for these downstream tasks, you will definitely get an improved output if you were to do a restoration first, because of the loss of color, because of the loss of so much of loss of the contrast, and all that stuff. Now, you also need depth, for example. So the previous task, right, would not really need depth, but then when you want to navigate, right, when you have a robot or something, an underwater vehicle, unmanned vehicle that is going around, in addition to the image, you also want to know where you are, where the other obstacles are in front of you, and that also means that you need a depth map, which should be actually good. And we know that predicting a depth map given a bad image, a degraded image, as you would get typically from an underwater camera, right, will not be an easy task. And again, right, one would like to get both a restored image as well as a depth map, right? So this entire talk is about how do you enhance visual tasks, right? I mean, or in terms of your visual understanding of the scene by actually recovering a cleaner image from a degraded image, as well as a depth map, right, which is actually enhanced, or which is more accurate, right, as opposed to what you would get directly from a degraded underwater image. And we know that, right, there are so many applications of this, including biological research, archaeology, environmental monitoring, and so on, underwater robotics, to mention a few. Now, I'm going to kind of talk about one of the works that we did recently, not so very recently, but in ICCV 23. So I'm going to summarize that work, and I'll give you a good sort of insight into what went into that work. And then, if possible, I'll also gloss over our recently accepted paper at the upcoming CVPR. If I get time, I'll also gloss over that just to say something more on underwater that we are doing right now. But in any case, right, so in this talk, I'm going to be focusing more on a self-supervised monocular underwater depth recovery, and then a restoration, and a real sea, a data set. So this paper was important is important from several aspects, in my opinion. So, for example, the key objectives were that what we found was, as I will talk right down the line, that either you had methods that were doing good depth map kind of prediction, or you had algorithms, which would try to restore images. So we wanted to do a dual task, which will be like getting both at the same time, and in a manner that one aids the other, and then simultaneously in real time. And also we wanted it to be really fast. We wanted a method that would work in real time, because most of the methods that were out there were not really real time, especially, but there was none that was doing both together. And we actually took it upon ourselves to do something that would be interesting in terms of both depth as well as image restoration. And what did we do? So the motivation stemmed from the fact that existing data depth estimation methods, if you just focus on depth, they either use haze or they use geometry, but not both. And there was not a single deep network that could output both a restored image and depth map. Then there was no real pad data. I mean, right? I mean, even today we don't have pad data for underwater restoration that you can do in a supervised way. And then we also realized, to our surprise, that there were no underwater video data sets, which could probably be utilized, in terms of extracting, extracting view geometry, and so on. So we went ahead and this is a proposal, right, that we had in that work of ours of ICCV 2023, where we actually proposed a network which we call which is actually an unsupervised which is underwater self-supervised recovery of depth and image. I mean, that's what this UseReadyNet stands for. It interestingly utilizes cues from both haze and geometry for underwater depth estimation. As I said, simultaneously outputs both depth and the restored image. It is completely self-supervised in the sense that we don't need a ground truth at all. And as we know, I mean, it's not also easy to get a ground truth, especially in underwater situations. And then, in addition, we actually proposed a real underwater video data set for the first time, which we call as DRUA. The full form is there in the ICCV paper. Basically stands for a data set for real underwater video data set of real underwater videos of artifacts. I mean, that's what this DRUA stands for. And so the SOTA, right, at the time, in 1.5 years ago, was something like this. I mean, you had kind of traditional prior-based methods, which were kind of not very good because of the assumptions that they were making. Then deep learning, zero shot was very slow. Supervised methods, I mean, could do either depth or image, but then there was no real paired data. These are all very synthetically driven. And the best choice, it seemed to be like, an unsupervised or a self-supervised approach, which could perhaps do both. And here is a brief summary, right? I won't go into this. This is all there in the paper. Now, let me kind of come to the method. I mean, how are we doing it in a kind of different manner? So we don't need a paired data set. We try to do it completely in a self-supervised way. And then we have a single network, right, that gives both and then real output. So to just give you a feel for what kind of time we are looking at, it's about per frame, right? It takes 18 milliseconds, which is very fast. And it combines, I mean, by the way, the deep learning as well as image formation model. So there is a network, and this network is physics inspired. So the idea, right, is that behind this network is something very simple. So the idea is that, I mean, so if you can see what I'm indicating too. So what you have is a monocular video during training. During inference time, you don't need a pair. You just need a single image. But during training time, we take adjacent frames captured using a monocular video, which is what we did. I mean, when we actually captured a DRUA data set, we actually went with when a diver went down, and then he had a camera, a monocular camera, and then he went around about 20 artifacts, which are interesting artifacts, in shallow waters, and then he took videos of these artifacts. These are all monocular videos, and the idea was that could we reconstruct these artifacts both in terms of their shape as well as the underlying clean image using an approach, right, which we call as completely self-supervised. And in this approach, what we do is we take two adjacent frames, which we know are not exactly identical. But what we do is we have a deep network, right? We have a deep network that has different modules within it. There's one that solves for the air light, which is the top, and then there's one which solves for the underlying radiance, which is what we call the scene radiance net. And then there is something that solves for the transmission map, both the direct transmission map as well as what comes out of the backscatter. And then we also have a beta net, which is supposed to be finding out the extinction coefficients. And then given that, right, we had to train these networks, we needed a self-supervision, right, because it's completely self-supervised. So the self-supervision losses were of the following type. So what we would do is we would expect these modules to kind of disentangle the input such that we can get the air light, the radiance, and so on. And then one of the losses that we would have in the self-supervision is to kind of combine these together using the image formation model that is down right on the slide. Use the image formation model to combine them and then compare with the reconstructed image, which is I1 rec with I1, right? That is one loss. The other loss that we have is a view synthesis loss, which we get from I2. So the other frame that we have from the monocular video, we pass it through the same SR net, and then we get a scene radiance, estimate of the scene radiance, which we call as J2. And then we know that J1 and J2 are related through a depth map as well as a rotation and kind of a translation because the camera is continuously moving. And we have a postnet which we train such that it will solve for a six-dimensional vector, which will be 3 rotations and then 3 translations. And then we use the transmission map that is estimated from here in order to estimate depth map, right? Using an analytical formulation, which we know, right? I mean, so the transmission map we know is related to the depth map through an exponential function. So we use the estimated transmission map to find the depth map, and then use the depth map to warp J2 to J1, and then this J1 hat is then compared with the J1 that was estimated from the top, right? And therefore, these are the two self-supervised losses. And there is kind of one more loss, right, which we have, that I'll kind of talk about. So really, during training, what we are doing is we have network 1, 2, 3, and there is a Gaussian blur, which is for the air light. So I1 and I2 are two adjacent frames that are going in, and then we combine them, and these are estimated by these networks, these quantities, and then these quantities are then combined, right, using the image formation, Hayes image, the underwater image formation model, which has an absorption component and then a scatter component, a backscatter component, in order to arrive at the I hat, right? In this case, it should be I1 hat ideally. And then in the top, you get the scene radiance. And then we take the second guy, pass it through the same network 1, get the scene radiance. And then from this attenuation map, which is this e power minus of beta d, from that we get a depth map. And then we kind of push this depth map and the posts, right, which we have obtained through the postnet in order to get J1 hat from J2. Right, so this is simply a view synthesis loss. It's a view constraint, and therefore we have kind of two losses which are self-supervised: one between I1 and I hat, another between J1 and J hat. And then during inference time, right, we don't need a pair. We just send one image, and then out comes the scene radiance and then depth map. Right, so basically that is the overall idea. And the losses for the network I've already explained, right? So self-supervision 1 and then self-supervision 2. In addition, we have a depth smoothness loss, which is a very standard loss. And then there is a channel-wise depth consistency loss, which is only saying that all the channels should be estimating the same depth, right? So with this, if you kind of test this network, right, in the following manner, then what you get are kind of what you can see as an output, right, is something like this, where on the left you have the input image. So this is like a monocular video, and what I'm showing is on a frame by frame basis, right, in terms of the output, right, that I'm showing this for every frame, right, that is being sent inside, you're finding the output. So this network works on a frame basis, takes only one frame at a time. And then on the extreme right is actually the kind of depth map, right, that the camera sees. And the nearby points are brighter, and then the farther points are darker. Because one of the things that we should realize is that we don't have a ground truth for this. So we have some no reference metrics and so on, right, that you can compute. And and then some more outputs right here. I mean, these are all videos that are available if you go to the Dhruva website, which is available by you can just fill up a form, a requisition form, and then you can actually download the data, which is about 1.5 GB, and it will have about 20 videos of these 20 artifacts, and then right, you can kind of build your own algorithm. So this is what the Dhruva has. It's a complete 360-degree, right? This one azimuthal view of the artifact. And on the left, I'm showing you how this artifact looks like. I mean, these are some interesting artifacts that are in shallow waters. And this is, in fact, the first ever underwater video, this one, that data set. It had to be curated and so on before it could be released. And then on the right is actually a 3D kind of a point cloud, which also tells what was the camera path, which the kind of right diver took. And at this point in time, let me also acknowledge Dr. Sundaresh and his team from NIO Goa, which is the National Institute of Oceanography, who are the people who actually went underneath. I mean, me and my students were just sitting on the surface on a boat, whereas the actual people that went and then who did the diving and then who took the videos are these people from NIO. And then of course this data set incidentally can also be used for other kind of applications. And then in terms of comparisons, we did comparisons on with the depth estimation work, several of them, many recent ones, restoration, again the same. And then we have a complete set of if you see the paper, there is an exhaustive set of experiments where we actually talk about what is the how we do both in terms of depth recovery as well as a restoration of the red image. And these are some quantitative metrics. And incidentally, right, squid and see-through are two depth data sets which do have a real depth map, a real in the sense that which is accurate up to a scale. And therefore, right, you can have any scale in where you can have the scale in metric to calculate how well you're doing. We trained our network on our data set, and then when we did testing on these unseen data sets, we still did very well. I mean, compared to, even though right, we had a network which hadn't seen squid data or the see-through data. In terms of restoration methods, there's nothing like really a ground truth. What we have is only a pseudo ground truth, which is for UIEB. For the other two, for Dhruva and RUIE, there's nothing like a ground truth. So only thing is we had some no reference metrics, which we again compared with a whole lot of methods. And then we also had this depth and restored. I'm also showing here some outputs from images, randomly grabbed from the internet, just to show that it is not very sensitive to the data that it has already seen, and it actually works very well. I mean, even on data sets that are not seen. Then let me just introduce you briefly to the follow-up work, which is called Seeing in Low Light. Right, it has been accepted at CVPR 2025, for which a decision came only a couple of days ago. So I'm happy to share with you that this work, right, this work deals with actually low light, as opposed to the one, right, that I showed earlier. And here the idea is that, right, you have really kind of low light videos. And in fact, right, in this case, what we did was we took actually, we took let me just show you. So we actually had a rig. We made a stereo rig wherein one of the cameras had a higher exposure, the other camera had a lower exposure, and we took a stereo data, actually, I mean, again, of artifacts, and of course, several artifacts. And this video was recorded in this manner, and then based upon, and then the normal lighting that we have with a larger exposure, that is what we use as a guidance for the other camera, which has a lower exposure. And then right, in this work, we actually show that right, with this kind of an arrangement. And then one of the key things that we bring in is the a Retinex model, wherein we kind of break down the radiance that you see in terms of lighting and reflectance. And then of course, you need to do a bunch of that is a bunch of other things which I'm not explaining here because it's fairly involved. But then just to say that the whole idea was to bring in a Retinex model into this low light kind of a situation in order to be able to see a restore as well as recover depth. Again, do the joint task, but then now even when the light is really low. And right, this is roughly the kind of idea, but then I'm not going to be talking about this in detail. Like I said, I'll be only glossing over this. I just wanted to give you a glimpse about how this works. So on the leftmost is actually the input video that we have actually, which is a low light video. And on the right side is actually a restored video that you get out of this particular method that I haven't talked in great detail. And then on the rightmost we have a depth map. And right, with that, right, let me also, and then right, this also runs very fast. It's about 16 milliseconds on a GPU of RTX, on a GPU like RTX 3090. So to kind of conclude, so I just talked about a recent work of ours, which is completely self-supervised, which uses only input underwater images for actually training, exploits cues both from haze and geometry for depth, and returns, of course, both depth and the underlying sort of the hopefully a clean image simultaneously. Then use ReadyNet, that is what we call it, emerges to be the best for depth recovery as well as restoration. When we kind of compared it with a bunch of techniques, each one tailored, in fact, for depth or for image, even it outperforms methods tailored for these individual tasks. Computationally very efficient, 18 milliseconds per frame. And then in the process, we also proposed a dataset Dhruva, right, which is now available and which is being used by more than 100 researchers worldwide. And I just wanted to tell you, which I've already mentioned, that this work has been extended now to low light images utilizing a Retinex theory. And we will also be releasing another data set, which we call the ULV stereo. So it is like underwater low light video. And this one will also be made available soon to the researchers of that work in the underwater domain. So with that, I think I'll conclude my talk. I hope I've been on time. Thank you so much.
Thank you so much. Yeah.
So we take questions on a very exciting talk. There's one question in the audience here. Yes. You want?
So how do you evaluate for the first data set? Is that zero depth? Right?
So the question was, how do you evaluate this?
Since the predicted depth was zero depth, not actual depth.
You want to just come here?
No problem. Yeah. Thanks for the talk. So how do you evaluate for the first data set? Because the depths that you're getting, so there's zero depths, right?
Yeah. Yeah, so the point is, right, so with respect to the underwater Dhruva data set itself, we don't have a ground truth at all. So which is the reason why I mean, what we did was we actually checked our method on squid data set as well as see-through data set for which ground truth is available. So the kind of quantitative analysis which we have done is with respect to depth data sets for which ground truth is available. For Dhruva, there is no way to evaluate the ground truth. We can only visually observe and then sort of hope that it's doing well. But then it's not just that. For squid and see-through, we've actually compared and we actually outperformed them, as I showed in that metrics table.
Thank you. Just to follow up, so then can we use the pseudo depth for any other task reliably, hopefully?
Can we use?
Like your Dhruva pseudo depths for other tasks?
I would actually think so. For example, right, you could probably, and what we also found is that if you use, I mean, if you try to use something like a foundation model, something like a dam or something, and then if you try to run it on our say restored image, then we get a depth map which looks very similar to what we have. So in that sense, that is another way to sort of verify that, right, what we have is good, and then you can still have a scale invariant metric, but then because that also is only a foundation model, so really, right, there's no ground truth in that sense. But yes, I mean, right, you can use the depth estimated from this, right? I mean, you could probably use it in order to generate a NERF model or something. You can use it for that, or for example, right, you can use it for say comparisons, and so on.
Thank you.
Any other question? Is there maybe one question? Otherwise, I might ask a question. So earlier in the competition discussion, we essentially discussed how does it help? How does image restoration help for downstream other tasks like object detection and semantic segmentation? So do you think this the approaches you showed for image restoration have they been shown to make object detection and semantic segmentation better compared to other image restoration methods?
Yeah, actually, you know what? I mean, in the CVPR paper, which I've not been able to share the entire set of results, we actually showed that if you do a restoration and then that if you try to use a foundation model such as a segmentation SAM or a DAM, you can actually show that on the restored image, the output, right, which you get, the segmentation map that you get is a lot more improved, right, than what you would get if you directly use the underwater image as captured. In fact, right, I mean, if you see the paper, it is there. I mean, we did downstream tasks. We did for segmentation. We did for a depth map. We showed in both cases that the restored image is actually useful. I mean, so surely yes.
Super interesting. Is there any last question? Otherwise, thank you again for the very interesting talk, and yeah, thanks for joining.
Thank you so much. Thank you.
Yeah. Thank you, Raju.
Thanks, Uma. Bye-bye.
Bye.
Right, we're gonna go to second last point. So it's gonna be the third keynote by Jingyu Song, researcher at University of Michigan, robotics. He has worked at a couple of companies that everyone knows, NVIDIA, Intel, and some other companies. And yeah, he's going to talk about building the foundation for embodied marine autonomy. Super excited to have you here in person. Just going to open your.
Yeah, hello everyone. Super excited to share some of our past project, current project on how we develop scalable underwater perception solutions, and those are together trying to build like the foundations for better marine autonomy. Before talk about technical details, just a quick introduction on me. I'm currently a third-year PhD student at University of Michigan. I'm serving as a research assistant at the Field Robotics Group and also the UN Center for Autonomous Vehicles. I'm interested in multimodal perception, state estimation, and mapping for mobile robots, which include like underwater robots and also autonomous vehicles. So as I mentioned about marine autonomy, so here is a like motivation example on why enabling marine autonomy is important. Here I show like 2 examples where like underwater unmanned vehicles can help with like environment monitoring and also shipwreck survey. And such solutions have benefits in like safety, cost, efficiency. Yeah. So the next question become like, is this like hard? This is like a figure from a very famous paper published in Science Robotics about the grand challenges within the next like 10 years. In this like paper, doing like achieving like marine autonomy is like a huge part of it. And so yeah, it's definitely hard. But before talking about how we develop solutions for that, I just want to quickly introduce some basic concept about like autonomy. So usually we do like we have like modular designs for like autonomy solutions, which include like perception, planning, and control. And the group I'm working in is more like interested in like perception. And under the perception, like big umbrella of perception, there are like multiple tasks within that. I listed some of them, but it's definitely not all of them. In the first half of today's talk, I've been talking about how we develop a multimodal state estimation and mapping solution that is also a low-cost solution to facilitate development. And in the second half of today's talk, I'll talk more about how we design a high-fidelity, scalable, and GPU-accelerated underwater simulator to construct high-quality digital twins. And this like simulator will be able to help a lot of tasks, such as listed here. Together, combining these 2 projects, we hope they will collectively build a solid foundation for enabling marine autonomy. We want to begin with one of the fundamental challenges with like state estimation and mapping for marine robots. So basically, vision is really unreliable as a navigation source in low texture environments. And even when the robots are serving like highly textured regions where the like vision-based localization methods can like track the robot well, robots can still lose tracking when moving over texture-less regions. And in underwater environments, such a mixture is like very common and it's like unavoidable. And here I show like an example where like the state-of-the-art SLAM method called OpSLAM3. It can track the robot pretty well when there are like not number of features that you can detect. As you can see, when the number of features like decrease, the trajectory like quickly like explodes. Another example here I show even suffers from like initializing itself into like a stable state to be able to track the robot well. Therefore, we propose a solution called we call Turtle Map. It's aiming for enabling real-time localization and dense mapping. Our contribution includes hardware and system design of a low-cost robot platform. We also develop a Postgraph-based state estimation package to fuse multiple sensors and achieve robust performance on low-texture environments. This framework is based on roles, so it's compatible with a lot of packages, and it can achieve like real-time dense mapping on a very low-cost embedded computer. So as an overview, 2 main contributions is we develop a low-cost robot platform, and also we propose a localization and mapping solution. So I'll talk about our hardware design first. So for underwater perception, when you want to include more sensors, usually it's how to make them waterproofing is a fundamental challenge here. As I said, as you might say, like we have a stereo camera, which is not like waterproof, and we also have an embedded computer. Therefore, we design a sensor enclosure to give to house the stereo camera and also an IMU and also the embedded computer. We have like Ethernet terminals to make it able to like communicate with like the electronics enclosure and the surface and our like topside laptop. So we want to maximize the scalability of the solution. So we choose like low cost solution. In underwater, when we want to like construct a map of the environment, usually we'll be like deciding between sonar versus camera. A typical imaging sonar will be able to also give you like depth measurements of the environment. And here is an example I picked online, which claims that it's a high performance multi-beam image sonar at a game changing price point, but maybe everyone can make a guess, but the actual cost of this sonar is like 9K, which is actually more expensive than the robot platform that we showed, the blue robot platform. So we look at the camera and we find like there's already a lot of like stereo camera options that are able to like construct, like give us like the depths pretty well. This is like a real-time. This is a real-time depth that's constructed from this that mini camera. So we hope to enable the application of this type of sensors underwater, so people can benefit from having a lower cost solution. Yeah, and the price for it is like only like $499. So it's definitely like a much cheaper sensor. But to use this camera underwater, it's important to do a recalibration of it. And it is like a very critical solution because, as you can see, if we use the default calibration due to the different medium of the water, the reconstructed the depth from the camera is not reliable at all. We tested the camera, the stereo camera depths using a artificial rock platform we have in the lab. As you can see, after our underwater recalibration, you'll be able to construct the plan pretty well and construct the overall shape of the rock. But the calibration is not easy underwater. Here I show like how we do this in our like test platform. This was where I collected some data for evaluating this solution. So and accidentally just like get dragged into the pool. But luckily we got pretty good results and calibration parameters from that day, and it works pretty well in our follow-up test. To do calibration, we tested multiple packages available online. We tested like the caliber. We tested like default calibration tool in MATLAB and OpenCV. There's also a lot of our calibration targets that can be used. After a lot of trials, we finally found this combination like works the best for us. So that's all for the hardware part. So now I'll talk more about how we design this software solution. So as you can see, in our localization stack, we use DVO, which is short for Doppler velocity log. It's used to estimate the linear velocity of the robot relative to the sea bottom. We also use an IMU to estimate the angular velocity and acceleration. A barometer is also used to measure the depth of the robot to the surface. And we fuse these three types of sensors in a post graph. So basically a post graph, it has two components, a graph and a vector. The post is the variable we want to estimate. So it's basically the state of the robot. And we use vectors to connect poses in the graph. So the vectors basically adds constraints based on the sensor measurements. So we have like DVO, we have IMU and parameter connecting in between like connecting in between poses and solve them. And each time when a pose is added to the graph, we launch like graph optimization to estimate the latest state of the robot pose. And in our localization step, it's actually a multimodal odometry within a pose graph. The parameter is used for estimating the depth. Some used for angular velocity acceleration. DL estimates the linear velocity. We implement this in like very well-known like graph optimization framework called GTSAM. It doesn't have official support for parameter and DVL, so we added our own like, customized factor implementation to that. After we achieve like a robust state estimation, we publish the states using like ROSE TF tool. And as you can see, after we conduct like accurate like underwater recalibration, we will be able to get like very accurate depth point count. We use open source real-time volumetric mapping framework called WACV to construct dense map. We did a real-world experiment to validate the robustness and the performance of the proposed turtle map. Here we conduct like a real-world experiment at the towing tank at the University of Iowa because they have a capture system that we can get like ground truth localization to evaluate our framework. It has this like artificial beach, so it's also adding some like difference in the distribution of the like bottom surface. And it's also a good place to evaluate if our framework can construct the map accurately. And this map will be helpful for like amphibious vehicles, surface vehicles to do like tasks such as a mode transition. It has a lot of areas that's a very low texture, and it also have a like an on-site wave generator so that we test our systems under the robustness of our proposed solution under environment disturbance. We tested our solution in two logs. The first log we didn't launch the wave, and we drive the robot to survey the tank, trying to get the most coverage of the and construct the map. The second log we launched the wave and test if it's robust against environment disturbance. There's only the like central region has like valid motion capture tracking, but we evaluate the overall. We evaluate our mapping over at a larger scale. As you can see, our proposed solution was able to outperform like a pure DVL odometry or like a common filter based solution and outperform them by a lot. Here's a qualitative trajectory plot. As you can see, our solution, the turtle map, as shown in red, from starting to the end, aligns with motion capture ground truth trajectory the best. Here's a like live demo showing like running turtle map in real world. This is from the first log where it doesn't have wave. As you can see, it can track the robot pretty stable, and the robot will do like ascending, descending. It will do like turning, and you can see like combining our proposed localization and the accurate depth prediction. They combine together, construct the map of the environment pretty well. In addition to just mapping the bottom surface, we also place the artificial rock you might have seen in previous log. So this also like demonstrates that our solution will be able to also capture like small objects in an environment. So this is a like overall qualitative result we have from the first log. As you can see, at a pretty large scale, our the map region matches pretty well with what we captured with our phone. It's known by the like 3D model that the bottom surface is flat, and you can see like the overall geometry of the constructed map is also like flat. It does also map the artificial beach, so that's also pretty helpful. So for example, the amphibious vehicle will be able to know the distance to the bottom surface to be able to execute like land to sea or sea to land mode transition. The rocky is also mapped pretty well. We have ground truth like 3D like measurements, and those measurements like the size matches pretty well with our ground truth measurements. So Turtle Map as a scalable and robust perception solution is we released our code and the data logs we captured. And it's getting a lot of attention from the community, and we really hope it will inspire future research on enabling more robust data submission and mapping. So that's all for the first half. Hopefully that Turtle Map will be able to like deploy robots in more environments that they are not capable of doing before. But in our second part, we want to address the cost of the high cost of data collection. As you can see here, as you can imagine, if we conduct like real world experiments to collect data in this type of environment, how resource intensive this will be, and it will also definitely also require like sophisticated hardware and controlled experience setup, and a lot of field work will be involved as well. And we have already seen a lot of like in other fields, there are like scalable and high fidelity simulators. For example, the eyesight lab, which is able to learn like good like policy models from simulation, policy and perception models from simulation and transfer into real world. The eyesight lab is part of the like eyesight sim NVIDIA Omniverse, and also the 3D workflow called Open Universal Scene Description. There is some like 3D workflows that's using this Open USD framework to achieve like filmmaking rendering quality. So it's definitely like a high fidelity like 3D workflow. But when we look at underwater domain, it can be found like, for example, the NVIDIA eyesight sim, it doesn't have any support for like underwater sensors, such as like it doesn't have support to model like underwater imagery. It doesn't have support for like acoustic sensors, including like sonars, GVL, lanterns. And some of the state-of-the-art underwater simulators are suffering from, for example, here, the Whole Ocean. It suffers from CPU-based like ray casting algorithm to like render sonar measurement. So as you can see, it's like pretty slow and not like super capable of generating large amounts of synthetic data. Here's a quick summary on state-of-the-art simulators. Whole Oceans, as I mentioned, it does have support for, it does model like realistic acoustic sensors, but there is no like realistic image formation model inside that. You might also see that like the fidelity of this simulation framework is kind of low. It doesn't have a GPU-based sonar rendering, so it runs like slow when you have to like render sonars, which is a very important sensor for underwater like navigation and scene understanding. Another simulator called UNavSim, it leverages Unreal Engine 5. It has pretty high fidelity in modeling like underwater imagery, but it doesn't have any support for acoustic sensors, thus making it hard to like generate like sensor measurement pairs. Therefore, we design a simulator called OceanSim, trying to make it a huge step towards a unified high performance simulator. It's based on NVIDIA eyesight sim, and it's definitely a part of the NVIDIA Omniverse ecosystem and the USD 3D workflow. Some key benefits will include like real-time ray tracing, high fidelity underwater image rendering. We also enable user-friendly 3D workflows powered by the OpenUSD, and we implement sonar rendering algorithms on GPU to leverage like parallel computing. And you also have like native support for ROS, so a lot of existing frameworks can be like seamlessly integrated. Here we show some of the diverse underwater scenes we support in OceanSim. This is a towing tank we usually do our data collection in real world. It's at the Marine Hydrodynamics Laboratory at University of Michigan. We collect 3D scans of the environment in air and put it in OceanSim. OceanSim is also we also have a shipwreck thing that will simulate some of the shipwreck survey tasks. And OceanSim is also validated to be able to interact with like online 3D assets properly. And you can definitely like create your own, and just as long as it's format supported by OpenUSD and NVIDIA Omniverse. Here we show something that's not achieved in previous simulation. That's like very efficient scene customization workflow. Here we directly import our the towing tank 3D model into OceanSim. And we can customize a lot of stuff. We can put like objects in it. There's a vast amount of available 3D assets in like ISSM and Omniverse. As you can see, we put the rock platform we used previously just in this scene, and we can like flexibly adjust its position, how it interacts with the scene. We can also put other like available 3D assets, so you can collect data for maybe like object detection, sedimentation underwater as well. Here we enable gravity, so that's why you'll see like you fall down. You can definitely make it like float. One benefit of the ISSM is like it's a very easy customization of the overall like 3D environment you want to do simulation. Another benefit is that we can outperform the previous solutions a lot in rendering speed. Here we show like with our GPU based sonar rendering, we can do this. We can generate this sonar image pairs in real world, and you can see like you can achieve pretty high fidelity as long as you have high fidelity like 3D models. And we'll also quantitatively compare against the previous civil art simulators. As I mentioned, the Hollow Ocean, it uses oak tree-based CPU recasting solution. So it also requires like a cache process as the first time you import a scene. While for like OceanSim, it doesn't require to do any like pre-processing of the scene to save cache. So you can like directly customize your scene and then start generating your synthetic data. And it does outperform the Hollow Ocean in like frame rate a lot. Another thing I think in previous talks or like presentations, people have talked about how underwater image will look different from in air. And we develop an image formation model that address attenuation and backscattering, and we also provide this user-friendly like graphic user interface, so that you can. I mean, we understand like the users want to simulate different water types, different environments that may have to require to tune the parameters. So we offer like a very easy tool that you can just interact. You can just tune the parameters and directly see the real-time rendering results. So combine all these benefits, OceanSim provides a possibility of efficiently building digital twins. Here is a comparison of a real world log and what we replicate in OceanSim. It's the same like towing tank 3D model, and we are able to generate realistic images, DVL measurements, sonar measurements from it. And this is played in as a role spec in using roles. So it also have like support for roles. And we hope OceanSim provides a huge step towards a high fidelity underwater simulator. We will be releasing its beta version, hopefully in March 2025. And this is a project website of it. There's like a quick form where you can put your email, so you will get like updates when we release a model or have like huge updates on features. The preprint of the OceanSim paper will also be available at that time. So a quick conclusion. Turtle map hopefully could deploy more robots in unexplored environments. It's the first robust data estimation and fence mapping solution in low texture underwater environments. It's also like open source, and we hope OceanSim could help to generate large scale, high fidelity and sensitive data set. And it's also powered by GPU, and it's a part of a fast growing ecosystem and has efficient 3D workflows. And definitely acknowledge all of my collaborators. This is a QR code to the lab page of our group. And I'm happy to take questions.
Thank you. Any questions? Regarding the old system, support only 4 dimensional or 5 dimensional?
Yeah, so the question is about if OceanSim supports multiple types of sonars. Yeah, that's a great question. Currently, we support the forward-looking image sonar, and we also support like just like a simplified model, like 1D, like a pin type of sonar. It's our ongoing work of adding support for example, like the side scan sonar, and since it will be open source, so hopefully we'll release that model soon as well. Yeah, but in the first release, it will be imaging sonar and the pin sonar. Yeah. Yeah. So for turtle map, so the question about like cost, I guess cost analysis of turtle map. So the additional cost would be like building an enclosure for housing the stereo camera and the embedded computer and also the stereo camera, because we assume like most of the underwater vehicles will have or like sort of have access to a DVL. That enclosure took us a lot, cost us a lot, because it's kind of the first prototype of that company. We collaborated with them to build that, but we released like key design details on our website. So we hope like people who have like access to lower costs like manufacturing will be able to like build that in like a much lower cost. That enclosure costs us like close to like $3K US dollars. I mean, in addition to that enclosure, the only cost would be just like the camera, which is $499, and the computer, which is $300. So yeah. Yeah, it's running on Blue Rock. Something like that. Yeah. Yeah, we definitely see people getting manufactured enclosure at a much lower price point. So if you have access to that, that'd be great. Yeah.
questions. The first one, the huge pool, the weight generator, like, do you have open access to that? Like, is it part of your research, or is it some location that you have and then plan and experience?
Yeah, I can answer the first one first. So it's about the test site we tested turtle map. It's a towing tank at the University of Iowa. They are part of that project funded by ONR. So that's why we can use their test site and collect data. But as I mentioned, we released the two data logs with our turtle map. So you will be able to use that for your own, I guess, research need. For example, if you want to add like more, like I guess like visual factors or loop culture into that feel free to use that. It's available here.
And the second question was regarding the ocean side. So like to replicate, let's say, enclosed environment, and you also show the shipwreck, and so like the maps can be quite large.
Yeah.
And is it like possible to interact with the environment and dynamically change it?
Yeah, so that's a good question. That's about how, I guess, in Ocean Sim, the simulated robot like interacts with the surrounding environments we put there. So currently, Ocean Sim is a perception-oriented simulator. So that means we don't model like too complex, I guess, dynamics in between objects and environments. Now all the environments are imported as like a rigid body. In our, hopefully the next version of a more unified version, we hope to add like fluid dynamics and also add more realistic like dynamics of the robots to hopefully enable like a direct transfer of like maybe like a policy model learned from it. So yeah, so as it stands now, Ocean Sim is a great simulator for generating like data for like perception for like state estimation. Yeah. Yes. Yeah. Anything basically. For example, as long as it's like an OBJ, like or like any like popular model, I think it's supported by the Zeppelin. Yeah.
Awesome, thank you. I have also a couple more questions, but let's do that another time just because of time. Thank you again. Yeah, the last point of today's workshop is going to be the teasers for the spotlight presentation of the accepted papers. So we're going to play a video back to back with 2-minute presentations. It's going to be 20 minutes. But hopefully you get at a glance if there's anything that's interesting to you. And later we'll have the poster session still, where you can talk to the authors if they're there in person. Sound good? Any question up front? No.
Hello, everyone.
Audio should also be shared.
Today I'm excited to present Autofish, a dataset for fine-grained analysis of fish. Autofish consists of 1,500 images of 454 fish with unique IDs. It comes with more than 18,000 segmentation masks and ground truth length measurements, filling a significant gap in the available data from the fisheries industry. One of the many contributions of Autofish is the use of similarly looking fish from the cod family, allowing for fine-grained classification. Motivated by the need of automating the documentation of catch and fishing vessels, the dataset was collected in a laboratory environment with a setup that closely resembles the conveyor belts found on them. The fish species present in the dataset are commonly caught in fisheries conducted in the North Sea. Autofish comes with a novel grouping system. The available fish were pseudo-randomly split in 25 groups, and a total of 60 images were collected for each. This results in multiple reappearances of every fish and variation in their positions and orientation. The system allows for multiple train test split configurations while guaranteeing no information leakage. It also makes it possible to perform re-identification experiments. As part of our work, we performed baseline experiments. We used mass-to-former for instance segmentation, resulting in an average 89.15 mean average precision. The model struggles only on very high occlusion images, and our data ablation study shows that it stabilizes at near peak performance at approximately 9 training groups. In addition to that, we implemented 2 different approaches to length estimation, one using skeletonization on the segmentation masks and one based on convolutional neural networks. The skeletonization is overall weaker than its CNN counterpart, but our study shows that it is on the high occlusion images where that effect is most prominent. As can be seen from the plot on the right, the results of both methods further improve if one considers the median over multiple instances of the same fish, highlighting the potential of unique IDs and re-identification. Thank you for your attention. We're always happy to answer any questions you have, so feel free to send us an email.
Hello everyone, I am Mahmoud Nabi Murad, PhD student at the University of South Florida. I will present our paper on camera-based intruder detection and monitoring of ship crew work hours. With advancement in technology, the number of crew members on ship has decreased while work hours have exceeded standard limits, which affects the work quality and the safety. To address this, we need an automated system to monitor working hours and enhance the security. In this work, we propose a model to detect the intruders on the ship and to estimate the work hours of the crew members. We also provided a dataset which contains the real CCTV video recordings. Our objective is to ensure the security and to reduce the reliance on the manual record for work hour estimation. Our video dataset contains more than 100,000 videos. The duration of each video is less than 7 seconds. In the dataset, we have total 26 crew members. After identifying the faces, we manually labeled each person. In our model, at the beginning, we have face detector which detect the faces. Then by using a face recognition model, we recognize the faces and record the ID and the timestamp. In the right side, we present the crew ID and the corresponding number of the images in the face dataset. Among 26 crew members, we use the top 9 crew members to train the face recognition model, and the other crew members are considered as the intruder in our model. Left table presents the performance of the model without the intruder in the test dataset, while the right table presents the performance of the model with intruder in the test dataset. The performance of the intruder detection model is quite good here. In this figure, we present the hourly timesheet of 2 crew members. The blue portion represents the present in that hour, while the yellow portion represents the absent. Our model has some limitations, but considering the impacts and the application, we believe that our model could be useful in this domain. Besides improving the performance, we will add fatigue detection with work hour estimation method in future. Thank you.
Hello everyone, my name is Aotian and I'm a PhD student from the University of Washington. Today I will be talking about our work on automatic fish age prediction using deep machine learning, combining otolith images, NIR spectra, and metadata features. For each fish sample, we collect FT-near spectroscopy data. For otolith images, we collect images of whole otoliths under a microscope. Finally, we also have additional associated data, which we call metadata. We collect this data for 2 species of fish, walleye pollock and red snapper. For pollock, we collected 4,379 samples, which we separated into 17 age groups. For red snapper, we collected 5,030 samples, split into 20 age groups. To combine all 3 data modalities, a simple method is to concatenate the embedding features from the 3 branches together before using one classifier head to perform the final age prediction. This method, however, is simplistic and fails to take full advantage of having different input data types, as there is no mixing of information from multiple modalities during feature extraction. Here, we try another method of merging the 3 data modalities inspired by generative AI. Rather than concatenating all 3 embedding features together, we use the metadata and spectral data features as a condition to aid in the image feature extraction. The idea is that under different conditions, the way our model analyzes the image changes. We tried 2 different ways to incorporate the condition into the image feature extraction. We call them version 1 and version 2. Here we present the model performance using a combination of different input data modalities and different network designs. The first three rows show the aging performance of each data modality individually. The next four rows show the performance of simple merged network design with different combinations of the three types of data inputs. Finally, the last two rows show the results of merging the three data modalities by using the spectra and metadata as a condition for image feature extraction. For both Pollock and ResNapper, the condition merge version 2 architecture resulted in better aging accuracy compared to simple concatenation. Here we break down the classification accuracy by age group. Starting from the low ages, accuracy is high due to both the abundant training data and the easily distinguishable features. As age increases, accuracy gradually decreases until a certain point where accuracy sharply drops and becomes erratic. This is age 11 for Pollock and age 9 for ResNapper. For the higher ages, this occurs because of the lack of training data and the marginal difference in otolith features, where even humans have difficulty distinguishing. This demonstrates that otolith age classification is still a challenging problem due to both the fine-grained categorization and long-tail distribution. Thank you for listening to our presentation, and if you have any questions, feel free to email me at azheng@uw.edu. Thank you.
Hi, I'm Maritime from the University of Zagreb, Croatia, part of the Lab for Underwater System and Technologies, and today I'll be presenting our work on vessel registration number detection, a solution designed to improve maritime surveillance and operational efficiency. Let's dive in. Did you know that Croatia is home to the largest charter fleet in the world? In addition, it was recognized as the most popular sailing destination in 2022. This makes maritime operations and vessel identification, like our work on vessel registration number detection, even more critical for efficiency and safety in this thriving industry. Our system was developed and tested in the Adriatic region. On the screen, you can see a demonstration of our system in action, showcasing its real-life performance in detecting and identifying vessel registration numbers with accuracy and speed. Our system was trained on a dataset of over 7,000 images, split into a standard 8:1:1 ratio for training, testing, and validation. The training process was powered by NVIDIA hardware and took several hours to converge. We tested three progressive methods to improve our system. The first method relied solely on out-of-the-box OCR software. The second method incorporated a custom-trained vessel detector based on YOLO. And finally, the third method added a custom text region detector, also built on YOLO, to further refine the accuracy of vessel registration number detection. Out of all the tested methods, the third method with added text region enhancement performed the best, as you can see in this row. Looking ahead, we plan to test newer versions of YOLO that have since been released, explore the emerging transformer-based detector architectures, and expand our datasets to further improve the accuracy and robustness of our system. We appreciate your time and interest in our work. If you have any questions or would like to learn more, feel free to reach out. Thank you.
Presenting this paper called Underwater Image Enhancement and Object Detection are poor object detection results on enhanced images due to missing human labels. Now, if you look at the two images here, we have an original image and an enhanced version of the same image. We trained two object detection models on the original images and another one on the enhanced images, and we compared the performance to find out that the enhanced detector is performing lower than the original detector. And we hypothesized that this could be due to missing human labels from the images. If you look at this image, it's missing this huge coral object over here, but if you look at the enhanced image, it's much easier to detect, and even the enhanced detector was able to detect it along with other fish objects that were not seen by the human annotators on the left. Another example over here, you can see that in the original image there is barely two apparent Echinus objects, but in the enhanced version you can see some Holitorian objects thrown on the seabed with much clearer object edges. So for humans, it's much better to go with enhanced images for annotation instead of working on the original images, especially that in many underwater scenes, underwater images suffer from severe degradation. And if you look at the detection results here, it's much better. The enhanced detector was able to detect much more objects, and those objects were unfortunately classified as false positives, although they are truly true positives, but that's because we have an inaccurate ground truth. If you'd like to see more about this, please come visit me at the poster presentation.
This work, titled MTRED, focuses on 3D reconstruction in the maritime domain and is in collaboration with Samuel Picasson and Arnold William from Shield AI. Maritime scenes are challenging to reconstruct due to the abundance of textureless regions from background ocean and sky regions and dynamic regions from waves in the ocean. With a focus on localization, mapping, and other physical applications, we aim to provide insight into the 3D reconstruction field in the maritime domain by jointly considering scene completion and reconstruction accuracy. Our first contribution is a novel 3D reconstruction benchmarking dataset, MTRED, which will streamline future research in this area. The next contribution is our novel perception-based metric coined DIFPS. And lastly, we also present a baseline study of existing reconstruction models, along with pre-processing methods to determine a recommended pipeline. The MTRED consists of video extracted images from 19 open source videos, and here we have a figure to illustrate each video. Covered scene types include ships, islands, and coastlines. We use this new dataset with a range of reconstruction models and pre-processing methods to obtain baseline comparisons. We then determine a pipeline which reduces unwanted artifacts and highlights a shortcoming of the common standard reprojection error in its poor sensitivity to artifacts. Lastly, we consider perception-based metrics and show that existing scores such as LPIPs lack sufficient sensitivity for scene completion. Considering this, we develop and verify that our proposed DIFPS metric is superior in its ability to jointly evaluate scene completion and reconstruction accuracy. Our code and dataset is available on GitHub here.
Hi, my name is Nengi Kwekwin Kenton Datsun, and I'll be giving a short highlight of our paper, Marine Event Vision, Harnessing Event Cameras for Robust Object Detection in Marine Scenarios. This work was done with Dr. Corina Barbalada. Our paper attempts to address the question, how can we detect objects in challenging marine environments despite effects such as low lighting, occlusion, and turbidity? We propose a modified generalized Hoff transform method suitable for event-based data in conjunction with connected components clustering to identify objects and features of interest. We performed a number of tests to detect the following objects in varying levels of lighting: an underwater robotic arm, a hydrophone, a mechanical fish, a rubber duck, and a toy mouse. Out of these, detections of the toy mouse was the only experiment performed out of the water. The target objects were identified over various periods of time. The model chosen for each object and number of events being processed influenced the accuracy of detection. Finally, our key contributions can be summarized as the augmentation of event representation by the integration of the principal direction of the event, the design of a modified generalized Hoff transform that is coupled with the clustering technique for object detection, and the usage of event-based data for detecting objects in marine environments.
Welcome to this official video presentation for the MaCVi workshop at WACV 2025. My name is Vito Paolo Pastore and I'm a researcher at the University of Genoa. Today I'm going to talk about plankton and self-supervision. First of all, we can say that study plankton is very important, as plankton microorganisms can be used as biosensors for environmental changes and pollution. They are the basis of the marine food chain, and they are responsible for the production of a large fraction of global oxygen. Furthermore, thanks to the development of technologically advanced acquisition systems, there is the availability of large amount of plankton datasets, either annotated and especially unannotated. So how can we exploit large collection of unannotated plankton images. This is a first question we are trying to answer with this work. And a requirement we have is that as retraining is likely to be necessary because plankton population have shifts that occur naturally or due to human activities. So we need computationally light solution. As such, in this work, we exploit self-supervised protocols for in-domain large-scale pre-training, so exploiting this large collection of plankton images to replace the commonly exploited ImageNet supervised pre-training. In our experiments on popular plankton benchmark datasets, we get competitive performance when using the Dino pre-trained model as a feature extractor and only training a shallow classifier. And these results confirm that self-supervised learning is a valuable alternative to ImageNet, capable of obtaining results on par with the state-of-the-art, where ensemble of convolutional neural networks fully fine-tuned are exploited for the task at hand.
Hello everybody, my name is Aves and I'm a PhD student at University of Pisa. I'm here to present you a paper in which we have discussed curriculum learning, weighted loss function and a novel evaluation metric for imbalanced starship classification. This paper is co-authored by my co-supervisors Marco and Davide. The problem with starship classification is that the data is imbalanced, it's scarce and it's of low resolution. We're using curriculum learning. So instead of traditional curriculum learning, we are dividing data into easy, moderate, and hard subsets based on the number of samples in each class. So the classes with most number of samples, they belong to easy subset, and the classes with least number of samples, they belong to hard subset, and so on. We applied two different types of curriculum learning algorithms. In curriculum learning algorithm B, we have this number of the classes in each subset has the equal number of samples. In curriculum A algorithm, which is imbalanced, here we have introduced the imbalance that exists in the real data. We have utilized 4 different loss functions. We have utilized 3 state-of-the-art deep learning networks. We have used 9 classes of full starship dataset. For evaluating the performance of model, we have utilized F1 score and accuracy, but we found out that they do not work well in imbalanced datasets. So we came up with a new evaluation metric, which is called imbalanced scorer. So our results suggest that curriculum learning was able to get better scores. We were able to enhance the F1 score by 9%, and we decreased the misclassification and increase the classification accuracy of our model. Whereas in terms of accuracy, we weren't able to increase, but it's fine because our data is imbalanced and accuracy does not represent much about the performance of imbalanced data. We're able to find out that VGG is the best model, curriculum B is the best strategy, and weighted cross entropy works fine for identifying more classes. In key contribution, we developed a curriculum learning framework. We introduced 2 curriculum learning algorithms, analyzed the impact of loss function, and validated the approach on state-of-the-art models. We want to extend our study to other domains, use advanced models, automate curriculum learning, and use the polarization information of SAR data. Thank you for listening.
Hi, today I'll be presenting our work on efficient object detection for maritime search and rescue missions with embedded devices in cooperation with the NGO Search Wing. In maritime search and rescue missions, the goal is to quickly detect people and boats in distress. This means we have to cover large areas cost efficiently, which is where UAVs with off-the-shelf embedded devices and computer vision methods come into play. In our work, we introduced the SearchWing dataset that was collected by SearchWing and contains high-altitude images in contrast to existing datasets, which makes covering large altitude areas way more feasible. However, this leads to tiny objects and makes the image downsampling not viable. In our work, we also introduce a new metric. We argue that it's most important to just predict the presence of objects, for example through centroid prediction, instead of having IOU-based metrics. Just by changing this metric, we show that existing baseline models already perform way better than expected. We then introduce a new model, Falcon Eyes, which takes high-resolution images and turns them into smaller tiles so that they can be processed on embedded devices with limited memory. We then use a backbone network, which is mobile one and has low latency for downsampling the image, and couple this with an attention parameter-free SIM-AM. Finally, we classify all the spatial locations in a downsampled image, which means that for each spatial location in a downsampled image, we classify it as one of the output classes if it contains the centroid of that class. We then optimize this loss function so that it penalizes predictions that are slightly off to the centroid less than those that are further away. And with this, we show that our model, even though it has significantly less parameters than existing baseline models, is able to have a similar performance while having significantly low latency, even on embedded devices such as the Raspberry Pi 5.
I guess you know what I wanted to say. I just want to thank every one of you, especially you, Arno. And we have a physical poster session now in the ballroom. Posters 1 to 12 are for our workshop. And yeah, see you guys soon. I'm happy to talk to you later maybe.
Yeah. Thank you, Benjamin.
Thanks, Uma. Thanks for introductions and the challenge.
Okay, thank you.
Did it work out with the